What if the universe isn't just a random series of events, but rather a meticulously structured system with hidden patterns waiting to be discovered? This idea challenges everything we thought we knew about the cosmos. Recent breakthroughs in cosmology are slowly illuminating the mysteries of what existed before the Big Bang, the event that marked the beginning of everything we understand about space and time. As we journey into these uncharted realms, we are forced to rethink our most fundamental assumptions, questioning the origins of the universe itself. We often hear about the vastness of space, the boundless expanse that stretches beyond our comprehension. But what if that infinite stretch of the cosmos is merely the latest chapter in an ongoing story? Could the universe be part of a larger, more intricate pattern, a cycle of creation, destruction, and rebirth? This theory takes us beyond the traditional understanding of the Big Bang, offering tantalizing glimpses into what may have come before. One of the most compelling ideas gaining traction is that of the cyclic universe. According to this theory, the universe may not have had a singular beginning. Instead, it could be part of an endless sequence of expansions and contractions, a never-ending cycle that constantly gives birth to new universes. This suggests that time, as we perceive it, may not be linear at all. In this vision, the Big Bang could be just one of many events in an eternal cycle, each one followed by a collapse, leading to the birth of a new universe. It's a fascinating thought, a universe without an absolute beginning, a cosmic rhythm that persists forever. But the cyclic universe is just one of many possibilities. Another widely discussed theory is that of the multiverse, a concept that suggests our universe is not unique. Instead, it is just one among countless others, each existing within a vast cosmic landscape. These universes could be entirely different from one another, each governed by its own set of physical laws and constants. In this framework, the Big Bang wouldn't be the origin of everything. It would simply represent the moment our particular universe emerged from a broader, multidimensional multiverse. Alongside these theories, there's a more radical hypothesis that our universe was born from a quantum fluctuation in a primordial state. Imagine a time before the Big Bang when the universe existed in a super dense, almost incomprehensible form, where the rules of conventional physics broke down. In such a state, quantum fluctuations could have sparked a critical instability, triggering a rapid expansion that we now call the Big Bang. This theory suggests that the origin of our universe may lie in the very fabric of quantum mechanics, where randomness and uncertainty are the fundamental drivers of cosmic events. However, these hypotheses remain just that, hypotheses. The truth about the universe's origins remains elusive, and it's important to acknowledge the limits of our current understanding. Our scientific models, particularly at the intersection of quantum mechanics and general relativity, are still incomplete. As we push the boundaries of technology and deepen our exploration of space, we may one day uncover new truths that challenge and refine these ideas. What remains certain is that modern cosmology has sparked a fascinating conversation about the nature of the universe, pushing us to question not just what we know, but what we think we know. The traditional Big Bang model, which proposes that the universe began from a hot, dense state around 13.8 billion years ago, has been the cornerstone of our understanding of cosmic evolution. But as our tools improve and our understanding deepens, scientists have started to entertain the possibility that the universe may have a far more complex origin, one that stretches beyond the event we call the Big Bang. One of the most intriguing possibilities lies in the concept of quantum gravity. This theory suggests that before the Big Bang, the universe might have existed in a radically different state, governed by a set of physical laws unlike anything we can observe today. Some theories propose that the universe emerged from a fluctuating vacuum state, a kind of nothingness that existed before the birth of space and time. Others suggest that the universe could have originated from a previous contracting universe, hinting at a cycle of cosmic rebirth, where each new universe builds upon the ashes of its predecessor. These concepts bring us closer to the idea that the universe is not a one-off event, but rather part of an ongoing cyclical process, a process that transcends time as we know it. As we continue to explore these mysteries, the lines between science fiction and science fact continue to blur, leaving us with more questions than answers. But the pursuit of these answers is what drives us forward, offering new perspectives on the nature of existence and our place within this vast, enigmatic cosmos. Ultimately, as we stand on the precipice of new discoveries, it's essential to remember that our understanding of the universe is always evolving. What seems impossible today may become a cornerstone of scientific knowledge tomorrow. The search for answers to the question of what existed before the Big Bang may yet reveal a far more complex and interconnected cosmos than we ever imagined. For now, we can only continue our quest for understanding, exploring the wonders of space, and embracing the mysteries that remain just beyond our reach. String theory, a prominent candidate for a unified theory of physics, opens up profound and mind-bending possibilities regarding the very nature of reality itself. At its core, it proposes that the universe we inhabit is not singular, but rather just one of many in a vast and complex multiverse. Each universe within this multiverse may operate under its own set of physical laws, dimensions, and histories. This radical idea transforms our understanding of reality, challenging the notion that the Big Bang was the absolute beginning of everything. Instead, string theory suggests that the Big Bang may have been more of a transition, a shift between different states of existence, as opposed to a moment of creation from nothing. In this narrative, the rapid expansion of the universe immediately following the Big Bang, known as cosmic inflation, plays an essential and critical role. This phase, during which space itself stretched at an unprecedented rate, raises fundamental questions about what could have triggered such an inflationary event. What existed before the Big Bang, and how do we conceptualize the conditions that could give rise to such a transformative moment in cosmic history? These are some of the most profound and unsettling questions scientists face. The implications of exploring a pre-Big Bang universe force us to rethink our most basic concepts of time, space, and existence itself. In this exploration, it becomes increasingly clear that the story of the universe might be far richer and more intricate than we ever imagined. Quantum mechanics, the field that governs the behavior of particles at the smallest scales, also deeply influences our understanding of the universe's origins, particularly the moments leading up to the Big Bang. Traditionally, physicists relied on classical physics to explain the early universe, but as they peered further into the extremes of this realm, it became evident that these models could not account for the strange, chaotic conditions that prevailed. This is where quantum mechanics steps in as a revolutionary framework, offering insights into the behavior of matter and energy under the most extreme circumstances imaginable. In quantum mechanics, particles do not behave in the way we are used to thinking about them in the macroscopic world. They can exist in multiple states at the same time, a phenomenon known as superposition. This concept might be crucial for understanding the state of the universe just before the Big Bang. Some experts speculate that the universe originated from a quantum fluctuation within what appeared to be an empty vacuum state. Even in the emptiness of space, energy fluctuates in unpredictable ways, which could have sparked the rapid expansion of space itself, a process known as cosmic inflation. These fluctuations, occurring at quantum scales, may have been the seeds of the universe as we know it. But quantum mechanics doesn't stop there. It introduces the principle of uncertainty, famously articulated by Heisenberg's uncertainty principle. This principle states that it is impossible to know both the exact position and the momentum of a particle at the same time. In the context of the early universe, this inherent uncertainty may suggest that the conditions leading up to the Big Bang were far more chaotic and unpredictable than we could have ever anticipated. This randomness inherent in quantum events could have paved the way for the rich and varied tapestry of matter and energy that later coalesced into stars, galaxies, and planets. The seemingly random nature of these quantum processes could provide crucial insights into the conditions that set the stage for our universe. As we dive deeper into these possibilities, one of the most exciting and at times unsettling implications of quantum mechanics is the idea of the multiverse. Some interpretations of quantum theory propose the existence of multiple, possibly infinite universes, each with its own distinct properties, dimensions, and physical laws. This notion challenges our deeply held belief that our universe is the only one that exists, pushing us to reconsider what we thought we knew about the cosmos. If such a multiverse exists, it raises the tantalizing question of what lies beyond the observable universe, beyond the Big Bang, and beyond what we can perceive. Quantum mechanics not only offers a lens through which to view the origin of our own universe, but also invites us to rethink the very fabric of reality itself. It suggests that the universe might be much stranger and more complex than we could ever have imagined. The very nature of existence may be far more intricate than anything classical physics could have anticipated. An equally fascinating concept in cosmology is the idea of the singularity, particularly when considering what existed before the Big Bang. A singularity, in the simplest terms, refers to a point in space where certain quantities, such as density and temperature, become infinite. In the context of our universe, this suggests that before the Big Bang, all the matter and energy we now observe was concentrated in an infinitely small, dense point. The forces of gravity at this singularity would have been so intense that they would have led to the conditions necessary for the Big Bang itself to occur. As we attempt to peer into the distant past of the universe, the mystery deepens. According to the Big Bang theory, the universe began its expansion from this singular state roughly 13.8 billion years ago. But what exactly happened at that pivotal moment? The further back we look in time, the more difficult it becomes to reconcile our understanding of physics with the conditions that might have prevailed at that moment. The singularity challenges our most basic understanding of time and space. While we perceive time as beginning with the Big Bang, the notion of before becomes increasingly nebulous. According to our current models, time itself may have emerged from the singularity, meaning that in a very real sense there may have been no before in any conventional way. This notion forces us to reconsider everything we know about time, existence, and the very origin of the universe. The Big Bang, far from being a simple moment of creation, may represent a profound transformation, a shift from one state of existence to another, driven by forces and conditions we are only beginning to comprehend. In this light, the pre-Big Bang universe and the nature of the singularity itself continue to be some of the most intriguing and challenging mysteries in modern cosmology. Moreover, theoretical physics has proposed a variety of intriguing models that attempt to unravel the mysteries surrounding what might have occurred before the monumental event we refer to as the Big Bang. These speculative theories invite us to imagine realms beyond our current understanding, challenging the very essence of space, time, and existence. One such theory suggests that the universe may have gone through an endless cycle of expansion and contraction, hinting at a multiverse scenario. In this model, singularities could serve as gateways or entrances, connecting different regions of time and space across various parallel universes. Such a view opens the door to fascinating possibilities where our universe might merely be one iteration in a grand cosmic cycle. Another captivating theory revolves around quantum fluctuations, which imply that the fabric of space-time itself may have experienced chaotic behaviors prior to the Big Bang. According to this perspective, the universe's birth might not have been a smooth, well-defined event, but rather a tumultuous process driven by the unpredictable and erratic nature of quantum mechanics. If this is true, it could suggest that the very foundation of our universe was shaped by quantum forces at a level that transcends our conventional understanding of reality. While these ideas remain speculative and unproven, they inspire continued exploration into the deepest mysteries of existence itself. Singularities, the focal point of these theories, continue to defy our understanding of the cosmos and the laws of physics as we know them. The very notion of a singularity, an infinitely small, dense point where time and space as we know them break down, forces us to rethink everything we believe about the origins of the universe. Such extremes of density and curvature push the boundaries of human comprehension, compelling both scientists and philosophers to ponder the fundamental nature of reality. As new technologies and innovative methods emerge, scientists are gaining unprecedented access to the universe's earliest moments. These advancements allow us to probe deeper into the conditions that existed before the Big Bang, further enriching our understanding of the cosmos. Yet, despite these breakthroughs, the mystery of what lies beyond the singularity continues to fuel not only scientific inquiry, but also profound philosophical reflection. Mathematical models serve as essential tools for physicists exploring the enigmatic conditions that may have existed prior to the Big Bang. These abstract frameworks allow researchers to venture beyond the limitations of direct physical observation, opening up pathways to hypothesize about an era when the universe was radically different from the one we now inhabit. The pre-Big Bang era, characterized by extreme conditions and unique states of matter and energy, presents a challenging puzzle. Without these complex mathematical tools, grasping the nature of these extreme environments would remain nearly impossible. A prominent example of such theoretical work is string theory, which proposes that the fundamental particles that make up our universe are not point-like entities, but rather tiny vibrating strands of energy. In the framework of string theory, physicists develop intricate mathematical formulations to understand how these vibrating strings might have behaved under the extreme conditions of the early universe. String theory provides a compelling way to reimagine how matter and forces could have interacted before the universe began its vast expansion. By shifting our perspective to view particles as one-dimensional strings, we gain valuable insights into the very fabric of reality and the forces that govern it. Another significant line of research revolves around the unification of two fundamental pillars of physics: general relativity and quantum mechanics. Physicists working on models of quantum gravity aim to bridge the gap between these two theories by incorporating elements of both into a single cohesive framework. This research is crucial for understanding how gravity, the force that governs large-scale structures in the universe, may have behaved in the unique conditions of singularities. The quest to understand quantum gravity also brings to light the possibility that the conventional rules of space and time may not apply in the extreme conditions that existed at the dawn of the universe. These models propose that our understanding of gravity and space-time may require significant revision in light of the universe's earliest moments. Cosmological simulations powered by advanced mathematical techniques allow scientists to create virtual universes to explore various initial conditions that could have led to the universe we observe today. By adjusting different parameters and observing the resulting virtual worlds, physicists can generate hypotheses about the potential scenarios of cosmic evolution, including those that might have characterized the era before the Big Bang. This powerful blend of mathematics and cosmology helps enrich our understanding of the universe's history and offers a glimpse into the vast possibilities of its early stages. The ongoing pursuit of knowledge in this realm continues to illuminate the dark corners of our cosmic origins. In considering the pre-Big Bang conditions, scientists also grapple with a far more abstract concept: the nature of time itself. Time, as we commonly understand it, is a measure of change, moments passing, events unfolding in a sequential order. But before the Big Bang, this conventional understanding of time begins to lose its meaning. The prevailing theories suggest that time, as we experience it, may not have existed in the conventional sense before the birth of the universe. Instead, time may have been bound up with other processes, deeply entangled with the fabric of space-time in ways we are only beginning to comprehend. To further explore this idea, it's essential to consider the conditions of the universe at the time of the Big Bang. Some researchers propose that the universe at this moment was compressed into an extremely hot and dense state. In this scenario, the very fabric of space and time were so intertwined that they formed a singular entity known as space-time. Without the universe as we perceive it, expanding and cooling, there may have been no time at all. This hypothesis suggests that the emergence of time itself might have been intricately linked to the moment the universe began its rapid expansion. In this view, time would have originated alongside the universe, marking the inception of both spatial and temporal order. These ideas continue to evolve, and as science progresses, we find ourselves confronting questions that may forever remain beyond our grasp. However, the relentless pursuit of understanding, fueled by both scientific and philosophical curiosity, ensures that we continue to search for answers, no matter how elusive they may be. The quest to uncover the origins of the universe is far from over, and each new discovery only serves to deepen the mystery of what existed before the Big Bang. Scientists continue to push the boundaries of our understanding of the universe, exploring groundbreaking theories to uncover the mysteries of its origins. Among these theories is the concept of quantum gravity, which aims to explain the conditions that existed before the Big Bang. These theoretical frameworks suggest that the conventional understanding of time, as we experience it, may break down at quantum scales. In place of a linear flow of time, where events unfold in a past, present, future sequence, the early universe might have operated according to a more intricate and complex interplay of events, an interplay that defies our traditional conceptions of time. This radical shift in understanding opens up the possibility that time itself might not have been an inherent property of the universe, but instead something that emerged with the universe's very creation. What does this mean for our understanding of existence? As scientists continue to investigate the pre-Big Bang era, they are not just searching for answers about time and space. They are grappling with questions that challenge the very nature of reality itself. The insights they uncover push us to rethink our place in the cosmos, prompting us to question everything from the origins of the universe to the fundamental laws that govern its behavior. In this quest to explore time and space, researchers are also delving deep into the so-called Planck era, a pivotal moment in the history of the universe. This era lasted for a fraction of a second, from 0 to approximately 10 to the power of negative 43 seconds after the Big Bang. During this infinitesimally small window of time, the universe existed in an unimaginably hot, dense, and small state. Under these extreme conditions, the laws of physics as we know them begin to break down, rendering this period a frontier for scientific inquiry, where speculation and discovery meet at the edge of our understanding. At this critical juncture, the universe's four fundamental forces, gravity, electromagnetism, and the nuclear forces, were likely indistinguishable due to the enormous energy levels at play. This suggests that these forces, which today operate independently, may have once been unified into a single force. Unraveling the secrets of this period in cosmic history could shed light on how these forces separated and evolved into the distinct interactions we observe today. As researchers focus on the Planck era, they are also confronting larger philosophical questions about the universe's origins, its structure, and its purpose. Theoretical physicists are exploring ideas rooted in quantum mechanics and general relativity, hoping to develop a coherent narrative of the universe's early stages. One such concept is quantum gravity, which aims to merge the two pillars of modern physics, quantum mechanics and general relativity, into a single theory. If successful, this theory could provide insights not just into how the universe began, but also into the nature of time itself. Yet, as scientists probe deeper into the mysteries of the Planck era, they are forced to consider more than just scientific implications. They must also confront profound questions about existence and reality. What was the universe like before time itself existed? What was the force that ignited the Big Bang, and what was its significance? This line of inquiry offers a deeper understanding of how the universe operates. Each new insight into the early universe is not just a scientific breakthrough. It's an invitation to reconsider everything we thought we knew about time, space, and existence. The investigation into the Planck era challenges us to rethink the very fabric of reality, urging us to explore not just how the universe began, but also how we fit into the vast, interconnected tapestry of existence. For centuries, the Big Bang has been viewed as the defining moment of the universe's birth, marking both the beginning of space and time. However, recent developments in theoretical physics suggest that this view may be overly simplistic. New theories have introduced the idea that the universe may have existed in some form even before the Big Bang, challenging the conventional understanding of the cosmos. Rather than a singular, one-time event, the Big Bang could be just another transition in an ongoing cycle of expansion and collapse, an infinite series of beginnings and endings that stretch beyond our comprehension. In one of the more provocative theories, the idea of a cyclic universe is explored. This concept proposes that the universe undergoes an endless series of cycles, each marked by a Big Bang followed by a cosmic collapse, only to be reborn once again. In this model, the Big Bang is not the absolute beginning, but rather a transitional point from a previous state, leading to a new phase of cosmic evolution. This radically redefines our understanding of time. Instead of a linear progression from past to future, time may take on a cyclical nature, with each universe's birth influencing the next in ways we cannot yet fully comprehend. In this context, the implications for causality are profound. If time itself is cyclical, then actions taken in one cycle could have reverberations in subsequent cycles, shaping the development of the universe in unexpected ways. This idea challenges traditional notions of cause and effect, urging us to think about the universe of interconnected cycles rather than linear events. Another intriguing theory draws from the principles of quantum mechanics to suggest that the pre-Big Bang universe may have been governed by quantum fluctuations, tiny, random variations in energy that occur at the quantum level. In this state, the very concepts of space and time as we know them may not have applied. Particles could exist in multiple places simultaneously, defying the fixed laws of classical physics. This view introduces a fundamentally unpredictable nature to reality, suggesting that the universe operates in a way that is deeply interconnected, yet inherently uncertain. These ideas push the limits of our understanding of reality, inviting us to reconsider the foundational principles that shape our perception of the cosmos. If the universe is indeed a vast interconnected tapestry woven from both time and space, then the implications of pre-Big Bang theories stretch far beyond the confines of scientific theory. They urge us to think about existence itself, inviting us to entertain the possibility that what we perceive as beginnings and endings may be merely the latest chapters in an ongoing, infinite story of cosmic evolution. Time, as we understand it, is deeply intertwined with the fabric of the universe. Our current understanding of time is largely shaped by the Big Bang, which is often considered the moment when both space and time came into being. However, a closer examination of the scientific evidence, particularly through the lens of relativity, suggests that time, as we know it, may not have existed before the Big Bang. In this view, time and space are part of a unified entity known as space-time, which itself emerged during the Big Bang. Before the Big Bang, the universe was in an incredibly hot and dense state, with all matter and energy compressed into a singularity. In this environment, the concept of time becomes problematic. Without a framework in which time could exist, the very notion of before the Big Bang may not have any meaning. This radical idea challenges the traditional understanding of the universe, suggesting that the Big Bang marked not just the creation of the universe, but the very beginning of time itself. Quantum gravity and string theory offer models that further support this hypothesis. These models propose that at the most fundamental level, the universe operates according to laws that are vastly different from our everyday experiences. They suggest that at the extremes of the Planck scale, where quantum effects dominate, time as we know it may break down altogether. This mirrors the singularity at the Big Bang, a point where our conventional understanding of physics ceases to apply. As scientists continue to explore the fundamental nature of time and the universe's origins, these theories push us to reconsider everything we thought we knew. The Big Bang may not have been the ultimate beginning. It could have been just another phase in a much larger, more complex cosmic cycle. Time itself may not be as fixed and linear as we once believed, and our place in the cosmos might be far more fluid and interconnected than we can imagine. The journey to uncover these truths has only just begun, and the answers may be even more extraordinary than we could have ever expected. The compelling evidence supporting the Big Bang theory extends far beyond the theoretical realm, with observational data like the cosmic microwave background radiation adding layers of credibility to the concept that our universe had a definitive starting point. This faint but omnipresent radiation is often referred to as the echo of the Big Bang. It's a remnant of the intense heat that filled the universe in its infancy. The cosmic microwave background acts as a snapshot from the universe's earliest moments, revealing vital clues about the conditions that prevailed shortly after its birth. It is more than just a faint background signal. It is a direct glimpse into the primeval universe, suggesting that a clear, identifiable beginning took place at some distinct point in time. In turn, this reinforces the notion that all events following this moment, our current existence included, are inextricably linked to that beginning. The idea that time itself might have begun with the Big Bang raises fascinating questions. Our conventional understanding of time has always been based on the assumption that it is a continuous, external framework that exists independently of the universe. However, when we look at the earliest moments of the cosmos, the fabric of time and space-time, appears to have undergone a fundamental transformation. Today, we understand space-time as a fabric that seamlessly weaves together the three dimensions of space with the dimension of time. Yet before the Big Bang, it is hypothesized that this very concept of space-time might not have even existed in any recognizable form. This idea forces us to confront one of the most perplexing questions in cosmology. What happened before the Big Bang, and how could time itself have emerged from this initial singularity? The conditions leading up to the Big Bang present a paradox that challenges our most fundamental theories of physics. It's widely believed that the universe, before its explosive birth, existed in an extremely hot, dense state, a singularity where temperature and density reached infinite extremes. Under these conditions, the laws of physics, as we currently understand them, break down. General relativity, the framework that governs our understanding of gravity and the structure of the universe, ceases to function in such extreme environments. This breakdown suggests that our understanding of space-time, too, may fail in the universe's earliest moments. Rather than unfolding along a linear timeline within a well-established spatial context, the very concept of time itself may have been in a state of flux, undefined, yet full of potential. Emerging theories, such as quantum gravity, aim to address this conundrum by attempting to reconcile the strange behavior of space-time at these extraordinary scales. Some scientists propose that space-time may have been more fluid and dynamic than we have ever imagined, stretching and warping in ways that are far beyond our current comprehension. In this view, the universe's early moments may have been characterized by a state of potentiality, where space-time was still in the process of coming into existence. As such, rather than being a static framework in which events unfold, space-time itself could have been part of a grander process, evolving as the universe took form. These ideas compel us to rethink the very nature of reality. The evolution of space-time, intricately tied to the universe's formation, reveals that the birth of the cosmos is not simply a singular event, but a continual unfolding. This reshapes how we view time itself, not as a linear progression leading from past to future, but as an ever-changing force that is deeply intertwined with the fabric of the universe. As we probe these mysteries, it becomes increasingly clear that the narrative of our universe's origins and what existed before the Big Bang could alter our understanding of physics in profound ways. Scientists are not only trying to find answers to these questions, but also rethinking the questions themselves as they endeavor to uncover the deepest truths about existence. Among the many theories that aim to explain the universe's origin, the cyclic model stands out as a particularly thought-provoking perspective. This theory challenges the traditional view of the Big Bang as a one-time event, suggesting instead that the universe experiences an endless series of expansions and contractions. According to the cyclic model, after reaching a point of maximum expansion, the universe will not fade into nothingness, but will instead contract back into a dense state, eventually triggering another Big Bang. In this cyclical view, the universe undergoes a never-ending cycle of birth, death, and rebirth, where time and space are not finite entities, but are continuously renewed and transformed. One of the most captivating aspects of the cyclic model is the idea that time may not have a clear-cut beginning and end. Instead, it could be infinitely cyclical, perpetually unfolding in a rhythm that stretches across epochs. Each cycle could represent a new iteration of the universe, potentially evolving with distinct physical properties or laws. This challenges our conventional understanding of existence and forces us to consider the possibility that our current view of time is just one chapter in a vast, unending narrative. Furthermore, this model suggests that certain features of the universe, such as the distribution of galaxies or even patterns in the cosmic background radiation, may persist across cycles. These cosmic memories could offer clues about the deeper connection between the past and future, creating a dynamic, ever-evolving tapestry where time and space are woven together by the universe's cyclical nature. This perspective reshapes not only our understanding of cosmology, but also our philosophical view of the universe. It invites us to reconsider fundamental concepts like the nature of time, the possibility of an eternal cosmos, and the very destiny of existence itself. By challenging the linear progression from a singular Big Bang to a definite end, the cyclic model paints a picture of the universe as an ongoing process of transformation, a cosmic dance that continually evolves and renews itself. Cosmic inflation theory takes this exploration of the universe's beginnings even further, offering a radical new perspective on its infancy. According to inflationary theory, the universe experienced an extraordinarily rapid expansion during the first moments after the Big Bang. Within fractions of a second, the universe expanded exponentially, growing from a size smaller than an atom to something the size of a solar system. This dramatic expansion smoothed out any irregularities in the early universe, leading to the homogeneity and uniformity we observe in the cosmic microwave background radiation today. Inflation provides an explanation for the vastness of the universe and its uniformity, something that the original Big Bang model could not fully account for. Moreover, cosmic inflation bridges the gap between quantum mechanics and cosmology, suggesting that tiny quantum fluctuations during the inflationary period might have been the seeds of the large-scale structures we observe today, such as galaxies and clusters of galaxies. This theory not only helps explain the universe's large-scale structure, but also raises intriguing questions about the nature of existence prior to the Big Bang. Some theorists propose that our universe is just one of many in a multiverse, a concept where countless universes exist, each with different properties and physical laws. These ideas challenge our traditional notions of time, space, and reality, suggesting that the very fabric of existence could be woven from multiple, parallel realities. Cosmic inflation, by providing a framework for understanding the universe's early development, also encourages us to think more deeply about what might have preceded the Big Bang. It feeds our curiosity about the origin of the cosmos, offering potential answers while simultaneously opening up new questions about the very nature of existence. Through this theory, scientists continue to expand our understanding of the universe, not just in terms of its creation, but also in relation to the vast, unexplored realms of possibility that lie beyond the boundaries of what we know. However, inflation introduces an exciting possibility: that our universe might be just a minuscule part of a much grander and more complex entity, the multiverse. The multiverse theory suggests that beyond our observable universe, there could be other regions of space, each potentially governed by its own unique set of physical laws. This radical hypothesis stretches the limits of our imagination, proposing that the cosmos we observe could merely be a tiny fragment of a vast cosmic landscape. The idea even speculates that countless Big Bang events may have taken place throughout this expanse, each giving rise to its own universe, with distinct properties and physical laws. One of the most captivating elements of inflationary theory is its ability to resolve several profound mysteries within the standard Big Bang model. For example, the uniformity of the cosmic microwave background, CMB radiation, presents a significant puzzle. Despite the observable universe being full of irregularities and variations, this radiation appears remarkably consistent across vast distances. The inflationary model proposes that, in the very early moments of the universe, it existed in a state of almost perfect uniformity, which was then rapidly stretched to the size of the observable universe. This expansion left behind a smooth, nearly featureless background, explaining the apparent homogeneity of the CMB. Furthermore, cosmic inflation sheds new light on the structure of the universe itself. According to this theory, tiny quantum fluctuations during the rapid expansion of space provided the seeds for the galaxies, clusters, and large-scale cosmic structures that we see today. These fluctuations, embedded in the fabric of space-time, were stretched over vast distances, serving as the blueprint for the cosmic web that now defines the universe's architecture. The effects of inflation reverberate through the distribution of matter, creating an intricate cosmic tapestry that continues to evolve. Thus, inflation not only refines our understanding of the Big Bang, but also challenges us to rethink the very nature of reality. It forces us to reconsider the origins of everything we see, from the stars and galaxies to the fundamental laws of physics that govern the cosmos. Scientists, recognizing the profound implications of this theory, employ a wide range of cutting-edge techniques to test its validity and explore its consequences for the larger structure of the universe. One of the most crucial methods used in the validation of inflationary models involves the study of the cosmic microwave background, CMB radiation. This faint relic radiation from the early universe provides a snapshot of the cosmos when it was just a fraction of a second old. By examining the minuscule temperature and density fluctuations within the CMB, scientists can infer critical details about the physics that drove inflation, such as its duration and the energy scales involved. These fluctuations act as fingerprints of the early universe, offering a direct window into the conditions of the cosmos moments after the Big Bang. In addition to the CMB, researchers are also looking for evidence of gravitational waves, ripples in space-time caused by the acceleration of massive objects. Inflationary models predict that these gravitational waves should have been generated during the rapid expansion of the early universe, leaving behind faint signatures that could be detected by sophisticated instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. Detecting these waves would provide compelling evidence for inflation and offer new insights into the nature of space-time itself. Scientists also use advanced simulations to model the evolution of large-scale cosmic structures, such as galaxies and clusters of galaxies. These simulations allow researchers to test how different inflationary scenarios would impact the distribution of matter across the universe. By comparing the predictions of these models with actual observational data from galaxy surveys, scientists can assess the validity of various inflationary theories. A close match between the theoretical models and the observed structure of the universe would lend significant support to inflation as a viable explanation for the early universe's rapid expansion. In recent years, missions like the Planck satellite have provided high-resolution maps of the CMB, further enhancing our understanding of the universe's early moments. The data from such missions offers unprecedented insights into the fine details of the cosmos, offering a deeper look at how inflation may have shaped the universe's evolution. As more data accumulates, scientists continue to refine their models, getting closer to unlocking the mysteries of the universe's explosive beginnings. Through these multifaceted approaches, researchers are making significant strides in validating and enhancing our understanding of the universe's birth. At the heart of inflationary theory is the notion that, in the instant after the Big Bang, the universe experienced an extraordinary exponential expansion. This sudden and extreme stretching of space-time provided the resolution to several major puzzles in cosmology, particularly the problem of the universe's homogeneity and isotropy. Homogeneity refers to the idea that the universe looks the same everywhere when observed on a large scale, while isotropy suggests that the universe appears identical in all directions. These properties are clearly visible in the cosmic microwave background, where tiny fluctuations are present but still show a striking degree of uniformity. Moreover, the concept of the multiverse offers a bold and transformative perspective on the origins of our universe. While inflationary models provide an explanation for the large-scale structure and uniformity of the cosmos, the idea of the multiverse challenges our traditional notions of what before the Big Bang might have been. It suggests that our universe is but one of many, possibly even an infinite number of universes, each with its own set of physical laws and conditions. This hypothesis opens the door to a vast array of possibilities about the nature of reality itself, with the potential to reshape our understanding of existence. In the multiverse scenario, The Big Bang is not the singular beginning of all things. Instead, it could be one of many such events occurring in a larger, ever-expanding cosmic landscape. According to this theory, the birth of different universes could stem from varying physical laws or initial conditions, leading to the creation of entirely distinct realms of existence. Some models even propose that our universe might have emerged from a parent universe, undergoing its own process of cosmic inflation, which then branched out into multiple parallel realities. This idea suggests that the history of existence is not a linear sequence, but rather a dynamic and ongoing interplay of many beginnings, some of which may have occurred long before our own universe came into being. In sum, the concepts of cosmic inflation and the multiverse provide a profound shift in how we view the cosmos. They challenge long-held assumptions about the origin, structure, and scope of the universe, and suggest that the universe we observe may be far more intricate and interconnected than we ever imagined. As science continues to explore these revolutionary ideas, we are gradually uncovering the mysteries of the universe's origins, each discovery expanding the frontiers of human knowledge and offering new possibilities for understanding our place in the vast cosmic expanse. Moreover, certain theoretical frameworks delve into the possibility that time, as we understand it, may not have always existed. Before the Big Bang, it is conceivable that there was a state of existence that transcended the concept of time altogether, or one that was governed by dimensions entirely foreign to our current understanding. This view posits that time itself might have been a later construct, one that emerged after the universe began its evolution. The idea challenges the very fabric of our reality and raises fascinating questions about the nature of existence before our universe took form. In this context, some physicists explore the concept of a cyclical universe, where the Big Bang is merely one event in a continuous cycle of cosmic rebirths. According to this theory, the universe undergoes a never-ending series of expansions and contractions, each one followed by the collapse of matter into a big crunch before another expansion begins. This vision of a cyclical cosmos offers a perspective that allows for the possibility of pre-Big Bang realities, ones that may have existed without the traditional framework of beginnings and ends. These cycles, theoretically, could stretch infinitely backward in time, rendering our understanding of cosmic origins almost irrelevant. As scientific understanding evolves, so do the theories about the origins of the universe, and the multiverse hypothesis provides an even more radical departure from our current views. This idea pushes the boundaries of what we consider possible and forces us to reimagine our place within the cosmos. It presents a compelling challenge, suggesting that our universe might not be unique at all, but rather just one among an infinite collection of universes, each with its own laws, dimensions, and constants. The multiverse theory invites us to look beyond the singular event of the Big Bang and consider a vast, interconnected cosmos filled with an endless variety of realities. Rather than being the beginning of everything, the Big Bang could be just one moment in a broader, more intricate structure. This framework opens up an exciting array of possibilities. Each universe could be dramatically different from the next, with variations in physical laws, dimensions, or even the nature of time itself. Such ideas stir both awe and curiosity, pushing us to contemplate not only the origins of our universe, but also the very fabric of reality that may exist across potentially limitless dimensions. One prominent interpretation of the multiverse is rooted in the inflationary model of the early universe. This model posits that in the brief moments after the Big Bang, the universe underwent a period of rapid expansion, so rapid that it left regions of space with varying properties. In these different regions, inflation occurred in distinct ways, creating isolated pockets of space that eventually developed into separate universes. Each of these universes would possess its own unique characteristics, its own set of physical constants, laws of nature, and dimensions. This concept suggests that our universe may simply be one bubble in a vast cosmic foam, with an infinite number of other bubbles, each representing a separate universe. The cyclic model of the multiverse takes this idea further, proposing a universe that is eternally reborn. In this scenario, each cosmic cycle ends in a collapse, a big crunch, only to be followed by the birth of a new universe in a fresh Big Bang. These cycles could go on infinitely, with each new universe emerging from the remnants of its predecessor. This ongoing process of expansion and contraction could give rise to universes that vary significantly in terms of their physical properties. In some, the laws of physics may be remarkably similar to our own. In others, they could be so different that they are unrecognizable to us. The notion of infinite cycles offers a vision of an ever-evolving multiverse, with each iteration bringing forth new possibilities and realities. String theory, which offers a quantum mechanical framework for understanding the fundamental particles of nature, further extends the multiverse concept. According to string theory, the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can vibrate in a multitude of ways, and each vibrational pattern corresponds to a different set of physical laws. Within this framework, it is suggested that there are potentially tens of thousands of distinct ways in which these strings could vibrate, each leading to a universe with its own unique properties. This landscape multiverse posits that the universe we experience is just one of an unimaginable number of possible realities, each with its own set of laws governing space, time, and matter. In this context, some universes may support life as we know it, while others may operate under completely alien laws of physics, rendering life impossible. The idea that the universe we inhabit is one of many, each with its own rules and possibilities, opens the door to an even greater sense of wonder and exploration. The very nature of existence itself could vary dramatically from one universe to the next. In one reality, time may flow differently. In another, the dimensions of space could be curved or warped in ways that defy our understanding. These possibilities challenge our fundamental assumptions about what is possible, urging us to think beyond the boundaries of our own universe and consider the profound interconnected web of realities that could lie just beyond our grasp. The multiverse theory is more than just a scientific hypothesis. It is a philosophical inquiry that touches on deep questions about the nature of reality, existence, and the limits of human understanding. It asks us to reconsider the very foundation of our knowledge and to imagine a cosmos that stretches far beyond the confines of the observable universe. As our scientific tools evolve and our understanding deepens, the mysteries of the multiverse may one day reveal themselves in ways that transform not just our understanding of the cosmos, but our very place within it. The concept challenges us to dream bigger and to contemplate the infinite possibilities that might exist in the vastness of reality. The idea of a quantum multiverse offers an exciting and deeply complex perspective on the nature of existence. This theory, which emerges from the fundamental principles of quantum mechanics, suggests that every time a quantum event occurs, one with multiple possible outcomes, the universe doesn't simply settle on one of those possibilities. Instead, it splits into distinct branches, each one representing a different outcome that unfolds in its own unique universe. This branching creates an infinite number of versions of reality, each of which mirrors a different possible scenario. Within this framework, the universe we experience is just one of many that could exist simultaneously, each reflecting a different path taken by the same fundamental processes. Looking further back, some theories propose that even before the Big Bang, our universe might not have been alone. Instead, a vast array of alternate existences could have been unfolding, each with its own set of physical laws and constants. These pre-Big Bang universes might have diverged from each other long before the birth of our own cosmos. As such, the quantum multiverse challenges the very idea of a singular origin for the universe, and instead suggests that the birth of our cosmos could be just one chapter in an ongoing cycle of creation, expansion, and possible rebirth, all unfolding within a greater multiversal framework. This theory holds significant implications for our understanding of cosmic origins. It implies that the conditions we observe in our universe, such as the presence of life, the formation of galaxies, and the existence of stars and planets, might not be as unique or as extraordinary as we once thought. If there are many universes, then it becomes far more likely that at least one of them would have the right conditions to support life. The multiverse theory provides a compelling answer to one of the biggest questions in cosmology. Why does our universe have the specific conditions that make life possible? The answer may lie in the existence of other universes, each with its own set of conditions, making our universe just one of many possible outcomes. One of the key ideas supporting this hypothesis comes from the theory of cosmic inflation. This concept posits that shortly after the Big Bang, the universe expanded at an extremely rapid rate, stretching space itself almost instantaneously. As this expansion occurred, different regions of space could have experienced inflation at varying rates, leading to the creation of bubble universes that are isolated from each other. Each of these bubbles could have distinct properties, such as different laws of physics, fundamental constants, or even dimensions. In some of these universes, conditions might align to allow for the development of life, while others could be entirely inhospitable. From the perspective of quantum mechanics, the many worlds interpretation also contributes to the idea of a multiverse. According to this theory, every quantum event, no matter how small, does not just result in a single outcome, but rather causes the universe to split into multiple branches, each one representing a different possible outcome. This means that for every decision, every interaction, and every moment in time, there exists a separate, parallel reality where an alternate outcome plays out. This concept radically challenges the classical notion of a singular reality, suggesting instead that an infinite number of universes could all arise from the basic principles of quantum physics. Despite its speculative nature, the multiverse theory has captured the imaginations of scientists and laypeople alike. While it remains difficult to test empirically, since it posits the existence of other universes beyond our observational reach, the theory has inspired a wealth of new ideas and ongoing research. It forces us to reconsider the very nature of reality and question how much we truly know about the universe we live in. Could it be that our universe is not the only one to exist? Could there be other realities, each shaped by its own rules and filled with its own possibilities? The notion that our universe could be part of a much larger multiverse is not only a tantalizing idea, but it also presents some intriguing lines of evidence. One of the most significant pieces of evidence comes from the theory of cosmic inflation. According to this theory, the universe underwent a rapid expansion right after the Big Bang, and during this process, different regions of space expanded at different rates. Some scientists suggest that this inflationary process could occur repeatedly, with new bubble universes emerging each time. These universes, although separated by vast distances, could still interact with one another in subtle ways, leaving behind traces in the cosmic microwave background, CMB radiation, the faint glow that remains from the Big Bang itself. If we can detect anomalies or patterns in the CMB that can't be explained by our current understanding of cosmology, it might suggest that these bubbles, these other universes, have interacted with our own. Such evidence could provide a crucial window into the existence of a multiverse, potentially allowing us to glimpse the vastness of existence beyond our own universe. Another avenue of support for the multiverse comes from string theory. This highly complex framework proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. According to string theory, the universe's properties are determined by the ways these strings vibrate. And because there are an enormous number of possible vibrations, the theory allows for vast variations in physical laws, constants, and dimensions. This opens up the possibility that our universe could just be one of many, each emerging from a different vibrational pattern. The mathematical structure underlying string theory provides a model with many dimensions and potential variations, creating a vast landscape of possibilities in which multiple universes could coexist, each with its own distinct properties. Additionally, the principles of quantum mechanics fuel the multiverse hypothesis. Quantum mechanics suggests that particles do not have definitive states until they are measured. This uncertainty leads to interpretations that propose that every quantum event creates a branching of the universe into multiple realities, each corresponding to a different outcome. With every decision, with every measurement, new universes are born, creating a reality where every possible outcome is realized. This theory resonates with the idea that universes could emerge from cosmic events, leading to the possibility that different realities have existed long before the birth of our own universe. While definitive evidence for the multiverse is still lacking, theories like cosmic inflation, string theory, and quantum mechanics provide a framework for exploring the potential existence of multiple universes, even ones that predate our own. If these ideas are proven to be true, they could forever change our understanding of existence itself. The concept of the multiverse challenges us to think beyond the singular Big Bang event and invites us to imagine a broader, more interconnected cosmic landscape where multiple universes can coexist, each with its own story to tell. The concept of the multiverse offers a transformative way to understand our universe, one that could help resolve some of the deepest mysteries about existence. Perhaps one of the most intriguing questions it addresses is the fine-tuning of our universe for life. In a cosmos so vast, with an infinite or near-infinite collection of universes, each with its own set of properties and conditions, the notion that life could arise in at least one of these realms becomes less surprising. Instead of being an isolated, improbable event, the emergence of life within our universe could simply be one of countless possible outcomes in the cosmic lottery. With this framework, our universe doesn't stand as a singular anomaly, but as part of an expansive ensemble of realities, each representing a different permutation of cosmic law and fate. This view radically alters the way we think about the cosmos. It challenges the traditional narrative of a single universe and instead invites us to consider an infinite tapestry of realities, each one with its own distinct story. As we delve deeper into the idea of the multiverse, it not only enriches our understanding of the origins of the universe, but also ignites a fundamental curiosity about the nature of existence itself. The boundaries of traditional cosmology are stretched as we probe these uncharted realms, pushing scientists, philosophers, and thinkers to confront age-old questions about reality, time, and the very fabric of existence on a grand cosmic scale. Within this intricate web of possibilities, the nature of the beginning of our universe becomes more elusive as we contemplate realities that may never have followed a linear path. Quantum gravity, a fascinating frontier of theoretical physics, offers another crucial lens through which we can explore the early universe, including what might have existed before the Big Bang. Quantum gravity aims to merge the principles of quantum mechanics with gravity, providing a framework that may explain the very conditions that predate our cosmic expansion. At the smallest scales, the fabric of space-time is far from smooth and continuous. Instead, quantum gravity suggests that space-time is discrete and subject to the uncertainty of quantum mechanics. In models that attempt to describe a pre-Big Bang universe, quantum gravity plays a pivotal role in revealing what might have occurred before the universe began its nearly 14 billion-year journey of expansion. Traditional models of gravity grounded in Einstein's general relativity break down in the face of extreme conditions like those thought to exist at the very beginning of time. Quantum gravity, however, posits that all particles and forces, including gravity, emerge from a fundamental quantum field. This understanding leads to the tantalizing possibility that the universe didn't begin from an absolute starting point, but instead underwent a different phase or state prior to the Big Bang. Some models, such as the cyclic universe theory, suggest that the Big Bang is not a singular event, but a transitional phase in an endless cycle of cosmic expansion and contraction. In this view, the Big Bang could be seen as a brief moment of rebirth within an eternal cycle, where quantum fluctuations during contraction trigger the birth of a new universe. This possibility invites us to reconsider the very nature of time and space, encouraging us to think about the cosmos not as a linear sequence of events, but as an eternal and fluctuating process. Quantum gravity also holds the potential to revolutionize our understanding of other key concepts in physics, such as entropy and causality. In the context of a pre-Big Bang universe, these ideas take on entirely new dimensions. Exploring how space-time behaves at quantum levels could unravel deeper connections between the microcosm and the cosmos. Theoretical physics pushes us to confront the unknown, revealing the profound complexities behind the birth and ongoing existence of the universe. String theory, another captivating area of theoretical physics, takes this exploration a step further by attempting to reconcile quantum mechanics and general relativity. It proposes that the fundamental building blocks of the universe are not point-like particles as traditionally thought, but instead tiny, vibrating strings of energy. These strings could exist in multiple dimensions, many of which lie beyond our usual perception and experience. In the context of the universe before the Big Bang, string theory suggests a fascinating scenario. It argues that the structures of space and time may have undergone a profound transformation from a higher dimensional state, referred to as the string landscape. In this model, the fluctuations and interactions of these strings could have set in motion the rapid expansion we recognize as the Big Bang. Rather than a singular, one-time event, the universe might represent just one phase within an ongoing process that involves the dynamic interplay of these strings across multiple dimensions. String theory suggests that the laws of physics themselves might have been drastically different during the early moments of the universe, or perhaps did not even exist in the way we define them today. Forces and particles as we understand them could have emerged from the intricate behavior of strings within higher dimensional spaces. This opens up new pathways for rethinking the nature of time in a pre-Big Bang cosmos, as well as how we approach the fundamental concept of causality. While much of string theory's vision for the universe remains speculative, it offers a tantalizing glimpse into what could lie beneath the surface of reality. It suggests that our universe might not be the sole reality, but merely one of many, each existing within a grand and interconnected multiverse. In this expansive vision, different universes could operate with distinct laws of physics, different constants, and even different dimensions. The very idea that we might exist in a multiverse with infinite possibilities challenges the established notion that our universe is the only one that exists. Instead, it opens up a universe of possibilities, where each reality could present a unique version of the cosmos, each with its own fundamental rules. This radical shift in perspective encourages cosmologists to look beyond our observable universe and to reconsider our place within a much larger and far more complex framework. It raises profound questions about the nature of reality itself, urging us to think about the universe not as a static, singular entity, but as part of an infinite collection of ever-changing, ever-evolving realms. The multiverse offers a deeply thought-provoking lens through which we can explore the vastness of existence and the very essence of cosmic reality. At the heart of this vision lies string theory, a leading candidate in the search for a unified theory of physics. This theory is revolutionary not only because it challenges our fundamental understanding of particles and forces, but also because it reshapes our view of the entire cosmos. According to string theory, the fundamental units of reality are not minuscule particles, but rather one-dimensional strings that vibrate in different patterns. These vibrations give rise to the particles and forces we observe, providing a new framework for understanding the complex dynamics of the universe. String theory also introduces the possibility of extra dimensions, suggesting that beyond the 3 dimensions of space and 1 of time that we experience in our daily lives, there may be up to 10 or 11 dimensions. While these extra dimensions are compact and cannot be directly perceived at the human scale, their effects ripple through the fabric of space-time, influencing the forces and phenomena we observe. This opens up the potential to explain phenomena that traditional models struggle to account for, including certain aspects of gravity and the behavior of fundamental forces. Furthermore, string theory invites us to reconsider our understanding of the multiverse. In this framework, the universe is not the only reality that exists. Rather, there are countless other universes, each with its own distinct laws of physics. These universes may have different values for constants, forces, and even dimensions, presenting an almost unimaginable array of possibility. This realization challenges our long-standing assumptions and encourages us to think in entirely new ways about the nature of the cosmos and our place within it. The notion of the multiverse, coupled with the theories of quantum gravity and string theory, invites us to venture into uncharted intellectual territories. It challenges the boundaries of our understanding, pushing us to rethink the origins and structure of the universe in ways that were once thought to be the realm of science fiction. As we continue to explore these ideas, we may find ourselves on the cusp of discovering an even deeper unity underlying the cosmos, one that holds the answers to the most profound questions about existence, reality, and the ultimate nature of the universe itself. The mathematical complexities embedded within string theory often push cosmology into a realm that is as speculative as it is intriguing. While traditional models of cosmology tend to focus on observable phenomena, relying heavily on empirical data and direct measurements, string theory takes a vastly different approach, one that operates in the abstract. This nature of string theory sometimes leads to conclusions that are difficult, if not impossible, to test using the current technological tools at our disposal. It creates a fascinating tension between the elegant beauty of the theoretical model and the practical limitations imposed by empirical evidence. This tension isn't merely a challenge. It serves as a catalyst for ongoing dialogue within the scientific community. As our observational technologies advance, there exists the possibility of uncovering new methods of testing these extraordinary ideas. These future discoveries might provide the concrete evidence needed to better understand the universe and its foundational principles. String theory, at its core, posits that the fundamental building blocks of the universe are not point-like particles, as previously believed, but rather tiny, vibrating strings. This radical shift in perspective brings with it a host of intriguing possibilities, especially when considering the conditions that might have existed prior to the Big Bang. In this speculative model, a pre-Big Bang phase could involve extra dimensions and unique energy states, creating a vastly different cosmic environment from what we observe today. But how could we possibly find evidence to support such a bold theory? One of the most compelling aspects of string theory is its potential to unify the forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. One avenue of proof would be the detection of gravitational waves, ripples in space-time that could reveal echoes from a pre-Big Bang universe. These gravitational waves could offer direct insights into the conditions that existed in the universe's earliest moments. Alongside gravitational waves, scientists have been studying the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. Any anomalies or unexpected patterns in the CMB might hint at the existence of extra dimensions, as string theory suggests. The search for such evidence is ongoing, as subtle clues in this ancient radiation might reveal interactions that transcend the familiar three-dimensional space we experience. Furthermore, string theory predicts the existence of exotic particles known as superstrings. These particles are thought to arise from the vibrations of strings and could potentially be detected in high-energy events. If particle accelerators like the Large Hadron Collider, LHC, were to observe signatures of these elusive particles, it could serve as a powerful confirmation of string theory's claims, suggesting that the universe is far more complex and layered than we currently understand. Such discoveries could offer tangible proof of a multidimensional reality, moving us closer to the idea that our universe is not a singular, isolated event, but part of a far more intricate, interconnected tapestry of dimensions and energies. Another key area of exploration is the study of cosmic inflation, the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. If models of inflation reveal any connection to the higher dimensional framework proposed by string theory, it could provide crucial clues about the universe's early moments. By reverse engineering the events that occurred before the Big Bang, scientists may be able to trace the origins of our universe back to its very first moments, potentially validating string theory's vision of a universe governed by additional dimensions and forces. At the heart of string theory lies its ability to bridge two monumental pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics, which describes the behavior of particles at the smallest scales, and general relativity, which explains the nature of space-time and gravity, have long been seen as incompatible. String theory offers a theoretical framework that unites these two seemingly disparate realms. By suggesting that the universe's fundamental building blocks are vibrating strings, String theory provides a fresh perspective that could potentially reconcile the differences between the quantum world and the cosmic scale of general relativity. In this speculative pre-Big Bang universe, the conditions would likely be radically different from anything we experience today. Traditional models suggest that at the moment of the Big Bang, there was a singularity, a point of infinite density where the laws of physics as we know them break down. String theory, however, offers a smoother transition through these early moments. It suggests that space-time itself could have been influenced by the vibrations of these strings, leading to a universe that is more interconnected and harmonious than we could have imagined. Before the Big Bang, the universe may have existed in a stringy state, where quantum fluctuations shaped the very fabric of the cosmos, laying the groundwork for the universe as we know it today. This theory also introduces the idea of extra dimensions, up to 9 spatial dimensions, beyond the 3 we can perceive in our daily lives. These additional dimensions are compacted, existing at scales so small that they are not directly observable. Yet, they play a crucial role in the unification of the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. String theory's broader vision posits that these extra dimensions and the vibrating strings that govern them provide the key to understanding the universe in a way that bridges the gap between the quantum and macroscopic worlds. If proven, string theory could fundamentally change our understanding of the cosmos, offering a more unified and coherent view of reality itself. At its core, the beauty of string theory lies not only in its elegant mathematical structure, but also in its capacity to describe a network of interactions that precede the classical understanding of time and space. It challenges our deepest assumptions about the nature of reality and opens the door to a more intricate understanding of the universe's origins and structure. As scientists continue to explore string theory's implications, both experimental evidence and novel insights may ultimately unlock new ways to understand the universe's formation, evolution, and very essence. Black holes, some of the most enigmatic objects in the universe, hold the potential to reveal profound insights into the nature of reality itself. These cosmic giants exert such immense gravitational forces that they warp both space and time, bending the fabric of the universe around them. Black holes are often thought to offer a glimpse into the deep mysteries of the cosmos, with some scientists proposing that they might even contain clues about the conditions that existed before the Big Bang. One particularly intriguing theory suggests that black holes could act as gateways to other universes or dimensions. According to this hypothesis, a black hole forms when a massive star collapses under the weight of its own gravity, creating a singularity, a point where density and gravitational forces become infinite. Some theorists speculate that these singularities may be connected to the events that took place before our universe came into existence. If true, black holes could serve as conduits, transmitting matter and energy from previous cosmic epochs or even parallel universes, opening up a whole new realm of possibilities for understanding the origins of the cosmos. This speculative view suggests that the universe we observe may not be the first of its kind, and the singularity at the center of a black hole may act as a bridge, connecting us to other realities beyond our own. The study of black holes, therefore, may hold the key to unlocking secrets not just about our own universe, but about the very nature of space, time, and existence itself. Moreover, delving into the radiation emitted by black holes, famously known as Hawking radiation, introduces a captivating layer of complexity to our understanding of the universe. This form of radiation, proposed by the legendary physicist Stephen Hawking in 1974, has far-reaching implications not only for black holes themselves, but also for some of the deepest puzzles in modern physics, such as the infamous information paradox and the true nature of space-time. Hawking's discovery challenges traditional views about how black holes behave, specifically with regard to how information is thought to be lost when objects fall beyond their event horizons. For centuries, black holes were believed to simply devour everything in their vicinity, never releasing any trace of matter or energy. However, the idea that black holes can emit radiation slowly lose mass, and ultimately evaporate, suggests a more dynamic role for these cosmic behemoths in the broader workings of the universe. If this radiation allows for the potential escape or transformation of information, it could revolutionize our understanding of the universe's history, even stretching back to a time before the Big Bang. Could there be a continuity to cosmic evolution, a cycle that transcends the singularity of the Big Bang itself? If information is not truly lost, then the universe might follow a more cyclical pattern, one that repeats and transforms in ways we have yet to fully comprehend. Although black holes do not directly provide evidence of the pre-Big Bang state, they undeniably push the boundaries of our current understanding. These enigmatic objects force us to confront the limits of our knowledge and spark an insatiable curiosity about the very framework that governs our existence. As scientists continue to investigate the mysteries of black holes, they uncover new theories that could bridge the gap between conventional cosmology and the unfathomable unknowns of the universe. This journey of exploration leads us into the theoretical world of white holes, the hypothetical counterparts to black holes. While black holes are known for their ability to draw everything inward, white holes would theoretically expel matter, energy, and even information. This contrast invites a slew of fascinating questions, especially when we consider the potential role of white holes in the origin of our universe. Could a white hole have been the source of the Big Bang? In this scenario, the universe might have erupted from a white hole, sending energy and matter into a void that existed before its birth. This model offers an entirely new perspective on what came before the Big Bang, challenging the notion of a singular beginning, and instead suggesting a universe that may have always existed, cycling through phases of creation and destruction. If white holes exist, they could provide a mechanism for the formation of galaxies, stars, and planets. Rather than a sudden eruption of matter from nothing, the energy ejected from a white hole could be the very building blocks that form the universe as we know it. Another intriguing possibility connects white holes to black holes through the concept of wormholes, a theoretical tunnel that links different regions of space-time. In this speculative model, matter sucked into a black hole might not simply disappear, but could be expelled from a white hole, potentially even in a completely different location or universe. This interconnectedness between black and white holes could point to a deeper cyclical nature of the cosmos, where matter is continually transformed and redistributed across time and space. While these ideas remain speculative and lack empirical evidence, they fuel our imagination about the cosmos and its origins. The nature of white holes challenges the limits of our understanding of physics and raises profound questions about the fate and beginnings of the universe. As scientists continue to push the boundaries of cosmology, these theories open up exciting new avenues of research that might one day unravel some of the universe's most enduring mysteries. Black holes, those mysterious and seemingly omnipotent objects where gravity is so intense that even light cannot escape, continue to captivate the imagination of scientists and laypeople alike. They hold the potential to transform our understanding of the cosmos, not just as regions where matter is destroyed, but as sites where the very fabric of reality may be rewritten. Recent studies suggest that black holes could be far more than simple vacuum cleaners of the universe. They might serve as gateways to other dimensions or even other universes altogether, potentially offering a glimpse into realities that transcend our own. At the heart of a black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. One of the most intriguing ideas to emerge from the study of black holes is that these singularities might not just be the endpoints of matter, but rather the beginnings of something new. When matter collapses into a black hole, it raises the question of what happens inside that singularity. Could it be a bridge to another universe, a doorway to a different state of existence? Some physicists propose that our own universe may have been born from the collapse of a previous universe into a black hole, suggesting a cyclical model of cosmic rebirth, where the birth and death of universes are interwoven in a perpetual dance. Equally compelling is the possibility that studying the quantum effects near black holes could provide us with clues about the conditions that existed before the Big Bang. The merger of quantum mechanics and general relativity, two pillars of modern physics that, until now, have remained largely incompatible, is one of the greatest challenges of contemporary science. By observing how matter and energy behave under extreme gravitational forces, scientists hope to uncover the very fabric of space-time itself, potentially revealing what the universe was like before it began to expand. Black holes, then, are not mere oddities of the cosmos, but key players in a much larger story, one that may illuminate the origins of the universe and the laws that govern it. The study of Hawking radiation adds yet another layer to this cosmic puzzle. This radiation is a direct consequence of the strange quantum effects that occur near the event horizon of black holes, where the fabric of space-time is stretched to its limit. Rather than being purely destructive, black holes are now seen as dynamic entities that play an active role in the cosmic dance, slowly leaking energy and matter back into the universe. This process of mass loss challenges the idea that black holes are one-way objects, absorbing everything that falls into them. Instead, Hawking radiation suggests that they might contribute to the redistribution of matter and energy, offering a tantalizing hint at the nature of the universe before the Big Bang. The discovery of Hawking radiation also has profound implications for our understanding of the early universe. The quantum processes occurring near black holes may mirror the conditions that existed in the very early stages of the cosmos, offering clues about the nature of space and time before the universe expanded into the form we observe today. Hawking's theory blends thermodynamics and quantum mechanics, proposing that the universe might have been born from a chaotic quantum field, where particles and antiparticles fluctuated in an unstable state. These fluctuations could have set the stage for the Big Bang, a sudden expansion that would bring the universe into its current form. As we ponder the implications of Hawking radiation for the pre-Big Bang universe, we are reminded of the inherent uncertainty that surrounds the origins of everything. The concept invites us to consider a universe full of potential, where the boundaries between reality and possibility are continually shifting. The study of Hawking radiation brings us closer to understanding the very genesis of the cosmos and the role black holes play in shaping its fate. Cyclical models of the universe offer an intriguing alternative to the traditional view of a singular one-time creation event known as the Big Bang. In these models, the universe does not begin with a singular point in time, but instead undergoes an endless cycle of expansion and contraction. According to this idea, the universe reaches a maximum size before collapsing in on itself in a process known as the Big Crunch. This contraction could eventually trigger another Big Bang, leading to the birth of a new phase of the cosmos. This cyclical nature of the universe suggests that what we perceive as the beginning of the universe may simply be one chapter in an eternal cosmic drama, a story of creation, destruction, and rebirth that has been unfolding for an infinite amount of time. In this view, each universe is not a singular event, but a stage in an ongoing cycle, where the end of one universe seamlessly gives way to the birth of another. The implications of this model are profound. Rather than a universe that appeared from nothing, we may be witnessing the latest phase of an endless cycle, where the cosmos is eternally reborn in a perpetual loop. This cyclical vision challenges everything we thought we knew about the origins of the universe and forces us to rethink the nature of time, existence, and the very idea of cosmic creation. Cyclic models of the universe offer an alternative vision of reality, one that challenges the conventional understanding of time and existence. Instead of a singular, one-time beginning, these models suggest that the universe has existed in a continuous, eternal loop of expansion and contraction. Rather than beginning with a single Big Bang, the cosmos may have undergone countless cycles, each marked by a rebirth following a cosmic collapse. This concept fundamentally reimagines our approach to the universe's origins, bringing forward a radically different perspective on how time and space interact. In the cyclic model, the universe is not born from nothing, but rather emerges from a preceding universe that collapsed into a dense state. The process begins with an expansion from a singularity, just as in the Big Bang model. But instead of progressing to a final, irreversible end, the universe eventually reaches a peak and collapses back into a dense, almost infinitesimal state. This collapse sets the stage for the next cycle, where quantum mechanics might allow for a bounce rather than a singularity, ushering in the birth of a new universe, a new Big Bang. Thus, in this eternal cosmic rhythm, each cycle is not an isolated event, but part of a continual process of cosmic rebirth. What is truly compelling about these models is their potential to address some of the biggest mysteries of the cosmos. For instance, they offer explanations for certain anomalies in our understanding of the universe that the standard Big Bang theory struggles to resolve. One such mystery is the uniformity of cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. The CMB is incredibly uniform, yet it also contains small fluctuations. In a cyclic model, repeated cycles of expansion and contraction could smooth out irregularities in the radiation over time, making the observed uniformity a natural outcome of the universe's recurring birth and death. This idea provides an alternative to the inflation theory, which posits that the rapid expansion of the universe after the Big Bang was responsible for the smoothness we observe in the cosmic background radiation. Moreover, cyclic models introduce a fascinating philosophical dimension, inviting us to rethink not only the origins of the universe, but also the very nature of time itself. In these models, time does not have a singular beginning or an ultimate end. Instead, it is a never-ending cycle of rebirths, with each universe giving way to the next in an eternal dance of expansion and contraction. This view challenges the traditional linear perception of time and opens up profound questions about the nature of existence. Could the universe be infinitely old, with no true beginning or end, constantly regenerating itself in an eternal cosmic rhythm? The cyclic model suggests that the universe is always in a state of becoming, never truly finished or fully formed. At the heart of these models is the idea that the laws of physics, such as gravity and thermodynamics, could behave differently during the extreme conditions of a contracting universe. Theoretical physicists propose that as the universe contracts, certain forces may undergo transformations that allow for a rebirth, a new beginning, free from the paradoxes and singularities that plague the Big Bang theory. In this scenario, the end of one cycle becomes the beginning of another, creating a never-ending loop where the cosmos continually renews itself. As we explore these cyclic models further, we also begin to see their potential to reshape our understanding of the universe's ultimate fate. The traditional view of the universe's future often hinges on the idea of a final, irreversible collapse or a steady expansion that leads to a heat death. In contrast, cyclic models envision an ongoing process of regeneration, where the universe never truly dies, but instead undergoes a constant process of transformation. This vision of eternal renewal offers a much more dynamic and fluid understanding of the cosmos, one that reflects the intricate and complex forces at work within it. The idea of a cyclical universe is not just a theoretical concept, but is rooted in real observational evidence. Beyond the cosmic microwave background, there are other clues that suggest the possibility of an eternal cosmic cycle. Some researchers have pointed to patterns in the distribution of galaxies, the structure of the universe, and even the fluctuations in the CMB as signs that the universe may have experienced cycles of expansion and contraction in the past. These patterns could represent the remnants of previous universes, long gone but leaving traces of their existence in the fabric of the universe itself. Moreover, the study of quantum mechanics and its application to the very fabric of space and time offers further support for the idea of a cyclic universe. In quantum theory, space and time are not continuous, but instead exhibit a discrete, granular structure at the smallest scales. This suggests that the universe may be fundamentally different from the smooth, continuous space-time described in classical physics. As the universe contracts, quantum effects could come into play, potentially allowing for a bounce rather than a singularity. This would prevent the catastrophic collapse that occurs in traditional Big Bang models and set the stage for a new cycle, bringing the universe back to life in a different form. In essence, the cyclic model of the universe offers a profound shift in our understanding of both the cosmos and time itself. It challenges us to think beyond the idea of a single isolated event as the origin of all things, and instead invites us to envision a universe that is eternal, always in a state of becoming. and constantly renewing itself. This model not only provides new answers to old questions, but also opens up entirely new avenues for exploration and discovery, expanding our understanding of the universe and our place within it. The more we delve into these theories, the more we are reminded that the cosmos is far more complex and dynamic than we could have ever imagined, and that our journey to comprehend it has only just begun. As we venture deeper into the vastness of space, the observations of supernovae and the rate of cosmic expansion continue to shed light on the universe's mysterious dynamics. These phenomena offer a window into the ongoing evolution of the cosmos, with increasingly compelling evidence pointing to the presence and influence of dark energy. This mysterious force is accelerating the expansion of the universe, pushing galaxies away from each other at an ever faster pace. Some theoretical frameworks suggest that dark energy may not be a constant, but rather fluctuate in cycles, influencing both the acceleration we observe today and a possible future deceleration that might lead to a dramatic collapse, a concept that opens the door to a new cyclical model of the universe. In this narrative, the interplay between the accelerating expansion of the cosmos and the gravitational pull of matter forms a captivating picture. It paints a portrait of a universe locked in a dance between the forces of creation and destruction, forever remaking itself. This idea is best captured by the cyclical universe theory, a concept that suggests the cosmos undergoes a continuous cycle of expansion, contraction, and rebirth. According to this theory, the universe could expand outward, eventually collapse inward, and then explode again into a new cycle, thus perpetually reshaping itself across infinite timescales. To evaluate the plausibility of such a model, scientists turn to both observational evidence and theoretical frameworks rooted in the fields of physics and cosmology. One of the most crucial pieces of evidence comes from the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation serves as a snapshot of the early universe, offering invaluable insight into its state and structure moments after its inception. Scientists have painstakingly mapped this radiation, hoping to uncover hidden patterns that might point to previous phases of the universe's existence. They search for traces of contraction or even the signatures of a prior universe, looking for echoes of cosmic cycles that predate the one we currently observe. Alongside this, the dust and structures scattered throughout the cosmos provide further clues about the universe's history and potential future cycles. The current distribution of galaxies, the evolution of stellar systems, and the remnants of past explosions all speak to the dynamic processes that have shaped the universe over eons. These observations help scientists understand how the universe might continue to evolve in cycles, potentially repeating the sequence of birth, death, and rebirth. However, observational data alone cannot tell the full story. Theoretical physics, particularly through models like quantum gravity and string theory, offers deeper insight into the nature of space and time, especially under extreme conditions. Some physicists propose that the universe may not be limited to a singular beginning, but could instead follow a bounce model. According to these models, the universe might undergo a contraction phase, where it collapses in on itself before rebounding and expanding once again. This challenges the conventional idea of a single, definitive beginning, and instead suggests that the universe may have undergone multiple cycles of expansion and contraction, with each cycle giving rise to a fresh iteration of cosmic phenomena. These ideas open up the tantalizing possibility of infinite cycles, each creating a new universe with unique properties and events. Yet, despite the fascinating implications of these theories, the question of a cyclical universe remains unresolved. While current data tends to support the idea of a single monumental expansion originating from an initial singularity, the Big Bang, the evidence is far from definitive. As our observational tools improve and our theoretical models evolve, scientists continue to explore the possibilities of a universe that is not static, but rather one that reinvents itself in an endless cycle of rebirth. Another key concept in cosmology that ties into these questions is the cosmological constant. This term, famously introduced by Albert Einstein in his equations of general relativity, represents the energy density of empty space, what we now associate with dark energy. The cosmological constant has profound implications for our understanding of the universe, particularly when considering its earliest moments. In many cosmological models, the universe is thought to have begun with the Big Bang, a rapid expansion from an incredibly hot and dense state. However, some theories suggest there may have been a period of accelerated expansion prior to the Big Bang itself. This phase, often referred to as the pre-Big Bang era, might have smoothed out irregularities in the cosmos, laying the groundwork for the highly homogeneous and isotropic universe we observe today. The presence of the cosmological constant hints at the possibility that the universe's expansion was driven by a form of energy even before the Big Bang, creating a dynamic and ever-evolving environment. This energy, associated with dark energy, could have provided the force necessary for the universe to expand at an accelerating rate, setting the stage for the Big Bang. The cosmological constant also provides a crucial clue for understanding the universe's current expansion. Dark energy, which makes up about 70% of the universe's total energy content, is believed to be responsible for the accelerated expansion we observe today. By studying the cosmological constant, scientists are piecing together a more complete picture of the universe's timeline, one that stretches far beyond the Big Bang into the very forces that shaped the cosmos even before that momentous event. As we continue to probe these deep questions, the implications of the cosmological constant extend beyond the early moments of the universe. They challenge our understanding of gravity, the fundamental forces of nature, and the very structure of reality itself. The search for answers is ongoing, with each new discovery adding another layer of complexity to our understanding of the universe's origins and its ultimate fate. As our knowledge grows and our tools improve, the mystery of the cosmos and its infinite potential cycles remains an exciting frontier in the pursuit of knowledge. As the universe continues to expand, the gravitational pull exerted by matter steadily diminishes. In contrast, dark energy, embodied by the cosmological constant, maintains its unyielding consistency. This delicate balance between the decreasing influence of matter and the persistence of dark energy may have shaped the universe's fate long before galaxies began to form and stars ignited. For centuries, cosmologists have pondered the enigmatic origins of our cosmos, and with each new discovery, the possibilities of what came before the Big Bang grow ever more intriguing. Researchers now delve deeper into cosmic history, seeking to understand whether the cosmological constant could offer crucial clues about the universe's pre-Big Bang state, or whether it might illuminate pathways to parallel universes altogether. This quest leads to a series of profound questions. Did our universe emerge from a previous phase, or perhaps it is merely one in an endless chain of cosmic rebirths? Could other universes, disconnected from ours in ways we cannot yet fathom, exist alongside our own? As each discovery layers new insights, our understanding of the cosmos grows, and so do the fundamental questions that challenge our perceptions of time, existence, and reality itself. The cosmological constant, a cornerstone concept in modern cosmology, holds the key to some of these mysteries. Initially introduced by Albert Einstein as a term within his equations of general relativity, the cosmological constant is now understood to be intimately connected with dark energy, a mysterious and invisible force that is propelling the accelerated expansion of the universe. In simplest terms, the cosmological constant can be conceptualized as a form of energy density, an invisible presence that fills all of space, exuding a repulsive gravitational effect that counteracts the attractive force of matter. This idea, once considered merely theoretical, has gained solid footing thanks to observations of distant supernovae and the cosmic microwave background radiation, both of which reveal something astonishing. Not only is the universe expanding, but it is doing so at an ever-accelerating pace. This revelation, an unexpected behavior that defied predictions, has compelled scientists to consider the presence of dark energy as the primary driver behind the expansion. And within this framework, the cosmological constant offers an elegant and simple explanation, making it the leading candidate for the force accelerating the universe's expansion. Yet, as much as the cosmological constant helps to explain the observable acceleration of cosmic expansion, It also gives rise to profound philosophical and scientific questions about the very nature of space, time, and energy. One of the most puzzling aspects of the cosmological constant arises from a disparity between the predictions of quantum field theory and the values we observe in the universe today. Theoretical calculations suggest that the value of the cosmological constant should be vastly larger than what we measure, leading to what is known as the fine-tuning problem. This discrepancy has spurred the development of various speculative theories attempting to explain the nature of dark energy and its role in the universe. Ideas such as quintessence, a dynamic form of energy that changes over time, or phantom energy, an even more mysterious form of energy that could have dramatic implications for the future of the universe, have been proposed. However, these theories bring their own set of challenges, further complicating our understanding of dark energy and raising new questions about the fate of the cosmos. Despite these challenges, the cosmological constant remains a pivotal concept in our ongoing quest to unravel the deeper mysteries of the universe. It acts as a window into the unknown, offering insights into the fundamental forces that govern the cosmos. But as we seek answers to the greatest cosmic questions, one critical hurdle remains: understanding the conditions that existed before the Big Bang. This enigma presents one of the most profound challenges in cosmology, primarily due to the inherent limitations of observational evidence. The Big Bang represents the very origin of our universe, the moment when space and time themselves came into being. As such, any conditions or events leading up to this moment remain steeped in uncertainty, making them incredibly difficult, if not impossible, to observe directly. The very nature of space-time before the Big Bang remains speculative at best. According to most cosmological models, the universe was once compressed into an infinitely dense point, referred to a singularity. However, this singularity represents a state in which the laws of physics as we understand them break down, leaving us with no reliable framework to predict or describe what the universe was like before the Big Bang. This absence of a clear physical model complicates the task of generating testable predictions about the pre-Big Bang universe. Even as theorists explore hypotheses such as cosmic inflation, which posits a rapid expansion of the universe just moments after the Big Bang, or cyclic models that suggest the universe undergoes a series of rebirths, there is still no definitive proof to support any one theory. These models may seem plausible, but without direct evidence, they remain speculative. Furthermore, one of the oldest and most significant signals we can observe today, the cosmic microwave background radiation, originates from roughly 380,000 years after the Big Bang. While this radiation offers a glimpse into the early, hot, and dense state of the universe, it provides no direct information about the universe's state before this epoch. As a result, scientists are forced to rely on indirect methods and creative theories to probe the mystery of what existed before the Big Bang. To make matters even more complex, the tools necessary to peer deep into these questions are still in their infancy. Advancements in technology and observational methods are crucial if we are to bridge the gap between what we know and what we can only speculate about. However, we are making progress. The development of high-powered telescopes has revolutionized our ability to observe distant galaxies, offering glimpses into the universe's past. These instruments allow us to trace the formation of galaxies and the early stages of cosmic evolution, bringing us one step closer to understanding the universe's origins. In tandem with these advancements, computational models have become an invaluable tool in cosmology. By replicating the conditions of the early universe, these intricate simulations allow scientists to test various hypotheses related to cosmic evolution. By examining the interactions between fundamental forces and particles, researchers can explore different scenarios of what might have occurred shortly after the Big Bang, helping us to refine our theories of cosmic inflation and other early universe phenomena. Particle physics is also playing a crucial role in uncovering the universe's origins. Particle accelerators, like the Large Hadron Collider, replicate the high-energy conditions that existed just after the Big Bang. By studying the particles created in these high-energy collisions, scientists can gain valuable insights into the fundamental building blocks of the universe, as well as provide a deeper understanding of phenomena such as dark matter and dark energy, two of the most perplexing and elusive mysteries in modern cosmology. As technology progresses, so too does our ability to explore the deepest mysteries of the universe, inching ever closer to unraveling the secrets that have remained hidden for so long. In this pursuit, cosmologists continue to challenge our perceptions of reality, time, and space, ever hopeful that new breakthroughs will eventually bring clarity to the vast unknowns that remain at the heart of the cosmos. Innovative technologies have unlocked an entirely new avenue for exploring the universe, with gravitational wave detectors leading the charge. These remarkable instruments, designed to measure ripples in space-time, provide a direct glimpse into some of the universe's most violent and mysterious events. Gravitational waves, the faint tremors caused by the cataclysmic collisions of objects like black holes and neutron stars, carry with them a treasure trove of information about these cosmic events. By detecting these waves, scientists are granted access to a wealth of data that significantly enhances our understanding of the cosmos, pushing the boundaries of what we know about the evolution of the universe. As these technologies continue to advance, the potential to probe deeper into the universe's origins grows ever more promising. With each new development, our understanding of the complex processes that led to the creation of the universe expands, offering a clearer window into its profound history. The implications of these advancements are profound, as they could help unravel long-standing mysteries about the early moments of existence and reveal the forces that shaped everything around us. In particular, scientists are eagerly anticipating several key discoveries that could reshape our understanding of the universe before the Big Bang. One of the most exciting areas of research lies in the cosmic microwave background radiation, CMBR, a faint but critical relic of the early universe. This radiation, which is the afterglow of the Big Bang itself, offers a snapshot of the universe in its infancy. Researchers are particularly interested in studying the subtle fluctuations within the CMBR, looking for anomalies or irregularities that might indicate the existence of events or phenomena that occurred before the universe reached its current state. These tiny variations could carry the imprints of cosmic inflation, the rapid expansion of the universe just after the Big Bang, or other phenomena that predate the formation of the universe as we know it. In addition to this, scientists are also turning their attention to the detection of gravitational waves that might have been generated in the universe's earliest moments. The ability to detect such waves, especially those originating from events that occurred during or just after the Big Bang, would be a powerful tool for testing theories about the very birth of the cosmos. These early gravitational waves could provide vital clues about what happened before space and time themselves came into existence. To detect these elusive signals, scientists are deploying cutting-edge observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and its advanced counterparts, hoping to decode the history hidden within these cosmic ripples. But the mysteries of the universe's origins don't end there. A significant portion of the universe's mass and energy content remains hidden in the form of dark matter and dark energy. Together, these enigmatic substances make up roughly 95% of the universe's total mass energy content, yet we know very little about them. Understanding how dark matter and dark energy influence the formation and behavior of cosmic structures is another area of intense research. Large-scale surveys, such as those conducted by the Vera C. Rubin Observatory, are expected to provide vast amounts of data on distant galaxies and their clustering patterns. These observations could offer indirect insights into the conditions that existed before the Big Bang, shedding light on how galaxies and other structures began to form and evolve. Moreover, advancements in particle physics promise to extend our understanding of the universe's earliest conditions even further. Experiments at particle colliders like the Large Hadron Collider, LHC, offer researchers the chance to probe the energy scales and physical conditions that might have existed in the moments following the Big Bang. By searching for new particles or interactions, particularly those predicted by theoretical frameworks like string theory or loop quantum gravity, scientists hope to reveal a deeper and more nuanced history of the cosmos. Such findings could challenge or even expand upon the traditional Big Bang narrative, providing a more intricate understanding of the universe's origins. As these groundbreaking observations unfold, scientists remain optimistic that they will illuminate the fundamental mysteries of the cosmos. These discoveries offer an unprecedented opportunity to explore the very fabric of reality itself, pushing the boundaries of our knowledge and reshaping our understanding of the universe. The technologies that make these observations possible are advancing at an extraordinary pace, and the next few decades could usher in an era of unparalleled revelations. Current space missions play a pivotal role in expanding our understanding of the early universe. Equipped with state-of-the-art instruments and technologies, these missions are offering a wealth of data that enhances our ability to study the formation and evolution of the cosmos. Crucially, observations conducted from beyond Earth's atmosphere allow astronomers to study cosmic phenomena without the interference of our planet's atmosphere, revealing the most detailed and accurate images of ancient stars, galaxies, and other celestial objects. For example, the recently launched James Webb Space Telescope, JWST, is a game changer in this regard. With its powerful infrared sensors, the JWST is able to detect light from galaxies that formed billions of years ago, offering an unprecedented look into the early stages of galaxy formation. The light captured by the telescope has traveled through space for eons, carrying vital clues about the composition and structure of these ancient galaxies. By analyzing this ancient light, scientists can reconstruct a timeline of galactic evolution, revealing how galaxies formed and began to cluster together. This is critical for understanding the expansion of the universe and offers insights into the forces that drove its growth. In addition to the Webb telescope, other missions, like the European Space Agency's Planck satellite, have also made significant contributions to our understanding of the early universe. The Planck satellite, for instance, has provided detailed measurements of the cosmic microwave background radiation. This radiation, which was emitted just after the Big Bang, holds key information about the universe's age, its rate of expansion, and the fundamental forces that shaped its early growth. By studying these remnants, scientists can gain critical insights into the forces that drove the universe's rapid expansion in the moments following the Big Bang. Additionally, missions that study extreme environments, such as those near black holes or in the aftermath of supernova explosions, are helping scientists understand the complex interactions of matter and energy. These extreme environments serve as natural laboratories for testing the limits of physics, providing a wealth of data that can shed light on the fundamental processes that shape the cosmos. Each new mission adds another layer of understanding, gradually revealing the intricate workings of the universe. As technology continues to advance, so too does our ability to observe the universe. With each breakthrough, the mysteries of the early universe become clearer, inviting us to ask more profound questions about the cosmos and our place within it. The ongoing quest to understand the origins of the universe and to explore the forces that shaped its evolution remains one of humanity's most exciting scientific endeavors. The second law of thermodynamics, a fundamental principle of physics, states that in a closed system, the total entropy, or disorder, tends to increase over time. This law has profound implications when applied to the origins of the universe, particularly the period before the Big Bang. According to this principle, the universe, over time, should evolve toward a state of maximum entropy. This raises intriguing questions about the state of the universe before the Big Bang. If the universe was once in a highly ordered state, what caused it to transition into the disorder we observe today? Could there have been a trigger that set the universe on its current trajectory? Or was there a different kind of cosmic balance at play? These are questions that continue to challenge our understanding of the universe's birth, inviting further exploration into the depths of time and space. Theories about the initial conditions of the universe present a vast array of possibilities, each with its own intricate and often bewildering implications. Some propose the existence of a singular, incredibly dense point, an almost incomprehensible cosmic seed from which the universe sprang. Others, however, take a far more complex approach. suggesting that the universe's origin could be entangled with concepts like multiple dimensions or even a multiverse, a sea of countless universes, each governed by its own set of laws of physics. Among these myriad hypotheses, one prominent theory is the cyclic model, which suggests that the universe is not a one-time occurrence, but rather part of an endless cycle of expansions and contractions. According to this view, the current state of our universe is not the absolute beginning, but the result of a prior contraction phase, followed by another Big Bang. This creates an elegant, perpetual loop, where the universe experiences moments of both chaos and order, with entropy, an overarching force of the universe fluctuating in intriguing and possibly incomprehensible ways. As the cosmos continues to unfold, one thing becomes clear. The rhythms of the universe may stretch far beyond the limits of our current understanding. Central to these theories is the second law of thermodynamics, which compels us to ask more profound questions about the nature of existence itself. What indeed came before the Big Bang? This remains one of the greatest mysteries of modern science, but our pursuit of this enigma drives us to explore ideas that push the very boundaries of what we know. The more we seek to understand, the more we find ourselves venturing into uncharted territories of both space and time. The pursuit to solve this cosmic riddle fuels our collective curiosity, propelling humanity forward in its quest to decipher the deep truths of the universe. One of the most critical concepts in cosmology, and one that challenges many of our assumptions about the universe, is entropy. Typically described as a measure of disorder or randomness, entropy plays a crucial role in understanding the evolution of the cosmos. In simple terms, entropy gauges how much energy within a system is unavailable to perform useful work. This concept is not just an abstract idea. It governs everything from the fusion reactions that power the stars to the eventual fate of galaxies, stars, and planets. Before the Big Bang, the universe is thought to have existed in a state of extremely low entropy. In other words, it was remarkably ordered and uniform. This notion challenges our natural intuition, as we often associate chaotic beginnings with a universe of disorder. But as the universe expanded and cooled, entropy began to rise, leading to the formation of galaxies, stars, planets, and the intricate structures we observe today. It was as though the universe gradually shifted from a pristine, ordered state into a far more complex and chaotic one, a process that has continued for billions of years. The idea that the universe might have started from such a low entropy state raises fascinating questions. Could it have originated from a singularity, a point of infinite density and temperature? This notion, when combined with principles of quantum physics, opens up a whole new range of possibilities. What could have existed before the Big Bang? What other phases or forms of existence might the universe have passed through prior to our current reality? These are the questions that continue to drive scientific inquiry today, keeping the mystery of our origins alive and ever present. Understanding entropy not only informs our discussions about the universe's origins, but also touches on some of the most profound and fundamental theories in both cosmology and thermodynamics. The delicate interplay between increasing entropy and the formation of order offers a tantalizing glimpse into the workings of the cosmos. As scientists continue to explore the universe's ultimate fate, the role of entropy remains pivotal in helping us grasp the universe's complex and enigmatic history, from its explosive beginning to the vast, infinite future that awaits. To fully comprehend the origins of the universe, it is essential to examine the nature of entropy, particularly in the context of the universe's early stages. In the brief moments following the Big Bang, the universe exhibited an astonishingly low level of entropy. This seemingly paradoxical condition raises significant questions. How could such a simple, uniform state evolve into the complexity we see today? And what processes allowed for this evolution? One widely accepted theory to explain this early low entropy state is cosmic inflation. According to this theory, in the moments just after the Big Bang, the universe underwent an incredibly rapid and exponential expansion. This phase of extreme growth effectively smoothed out any irregularities and led to a homogeneous and isotropic cosmos. In other words, the universe was nearly identical in all directions. As this inflationary period unfolded, it transformed the universe into a highly ordered system, which laid the groundwork for the formation of galaxies, stars, and all the structures that would eventually shape the universe as we know it. Another fascinating theory focuses on the concept of gravitational entropy. Unlike typical forms of matter, which generate disorder as they cool, gravity encourages the opposite effect. Dense regions of matter collapse and cluster together, forming galaxies, galaxy clusters, and other large-scale cosmic structures. This process effectively increases the universe's overall entropy over time, suggesting that although the early universe was low in entropy, it contained the seeds for tremendous disorder as matter condensed under the influence of gravity. This dynamic points to the possibility that, even in its earliest moments, the universe harbored within it the potential for immense complexity and unpredictability. But these are not the only explanations. Some scientists propose that the early universe may have had even more unique characteristics, ones that are not fully understood yet. Quantum theories, including speculative ideas such as string theory, leave open the possibility that the initial conditions of the cosmos were far more intricate and mysterious than we can currently comprehend. With each new discovery, new layers of complexity are revealed, shedding light on the universe's earliest moments and perhaps the very nature of reality itself. Among the most powerful tools in exploring these theories is the cosmic microwave background (CMB) radiation, often referred to as the afterglow of the Big Bang. This faint radiation permeates the universe and offers a snapshot of its infancy, roughly 388,000 years after the monumental event. It provides a rare glimpse into the conditions of the early universe as it transitioned from an opaque, ionized plasma to a transparent expanse, allowing light to travel freely for the first time. This transition marked a pivotal moment in cosmic history, setting the stage for the evolution of the universe. The CMB is not only crucial for examining the early universe, but also raises intriguing questions about the conditions that preceded the Big Bang. One of the most fascinating ideas is that the universe might have undergone a period of inflation, a brief yet rapid expansion that accounts for the striking uniformity observed in the CMB. It also explains the tiny fluctuations in temperature across the radiation, which are thought to correspond to the seeds of all future cosmic structures, galaxies, galaxy clusters, and the vast networks of matter that populate the universe today. Through detailed analysis of the CMB, scientists have begun to uncover insights about the fundamental composition of the universe. By studying the subtle variations in temperature, known as anisotropies, researchers have inferred the relative amounts of ordinary matter, and dark energy in the cosmos. These findings are essential for developing models that describe the evolution of the universe. But they also suggest the existence of phenomena that extend far beyond our current understanding, hinting at the possibility that the pre-Big Bang universe could have been influenced by forces or dimensions yet to be discovered. As new observational data continues to pour in from specialized observatories and satellites dedicated to studying the CMB, we move ever closer to answering the profound questions surrounding our origins. Every new discovery helps to refine our models of the universe's evolution and perhaps brings us closer to understanding the fundamental nature of reality itself. The CMB, with its intricate patterns and fluctuations, remains a critical tool in our ongoing quest to unlock the mysteries of the universe, not only regarding what followed the Big Bang, but also what might have preceded it. One of the most compelling features of the CMB is the anomalies it contains, slight temperature variations that provide significant clues about the universe's earliest moments. These variations, often linked to gravitational waves from the inflationary phase, offer support for models like the cyclic universe, which posits that the cosmos undergoes endless cycles of creation and destruction. These fluctuations hint at the possibility that density variations, perhaps even cosmic structures, existed long before the Big Bang, providing evidence for realities that stretch beyond the temporal boundaries of our current universe. Conversely, these anomalies can also generate skepticism towards certain pre-Big Bang models, particularly those that predict a simple, smooth universe. The irregularities observed in the cosmic microwave background, CMB, sometimes more concentrated in specific regions, hint at the possibility of complex processes that may have occurred before the emergence of our universe itself. This complexity, as revealed by the patterns in the CMB, aligns much more closely with the inflationary model of the universe rather than with a static or overly simplistic pre-Big Bang condition. Ultimately, the cosmic microwave background serves as a crucial piece of the cosmic puzzle in modern cosmology, its anomalies providing both support and challenges to existing theories about the origins of our universe. As our observational techniques evolve and new data emerges, the insights gleaned from the CMB will continue to reshape not just how we understand the birth of the cosmos, but also what may have existed before its inception. The CMB, often referred to as a remnant glow from the early universe, is a relic of the cosmos from just a few 100,000 years after the Big Bang. This faint radiation, which permeates the entire sky, offers a snapshot of the universe in its infancy, when it was still a hot, dense soup of particles. Through careful study, scientists have uncovered critical information about the conditions that prevailed during this time, offering an invaluable window into the birth of our universe. Detailed observations of the CMB, particularly its tiny temperature fluctuations, have revealed essential clues about the composition of the early universe. These fluctuations correspond to regions of differing density, which eventually gave rise to the formation of galaxies and large-scale structures that define the universe we observe today. This data has proven instrumental in helping scientists estimate the relative amounts of ordinary matter, and dark energy within the cosmos, ultimately painting a clearer and more precise picture of its overall composition. Moreover, the CMB provides compelling evidence supporting the inflationary model of the universe. This theory posits that, within the first moments after the Big Bang, the universe underwent an exponential expansion, rapidly increasing in size. The patterns observed in the CMB align remarkably well with predictions made by the inflationary model, lending further weight to our understanding of how the universe transitioned from a smooth, homogeneous state to the complex and structured cosmos we see today. The study of the CMB also allows scientists to investigate some of the most profound questions about the future of the universe. By analyzing its temperature and polarization, researchers can gain insights into the cosmic expansion, offering clues about whether the universe will continue to expand indefinitely or eventually contract. In this sense, the CMB serves as not only a reflection of the universe's earliest moments, but also a crucial connection to its ongoing evolution and ultimate fate. Pre-Big Bang theories, on the other hand, venture into even more speculative territory, challenging our current understanding of time, space, and reality itself. These theories often propose radical ideas about what might have happened before the Big Bang, such as the concept of a cyclic universe in which the cosmos undergoes endless cycles of birth, death, and rebirth, or the possibility of quantum fluctuations occurring in a timeless state. Such ideas force scientists to reconsider the boundaries of traditional scientific methods and urge them to explore new, abstract avenues of inquiry. One significant consequence of these pre-Big Bang theories is that they challenge the very nature of evidence in cosmology. Traditionally, scientific inquiry relies on observable data to construct theories and models. However, since the realm preceding the Big Bang lies beyond our current observational reach, researchers are left to explore more abstract theories and speculative ideas, often relying on tools and frameworks from fields such as quantum physics and general relativity. While direct observation of the pre-Big Bang era remains elusive, these innovative approaches open new possibilities for understanding the deepest questions about the nature of reality itself. Additionally, pre-Big Bang models challenge the linear conception of time and causality that dominates much of modern science. If time itself began with the Big Bang, then many of the standard methodologies of experimentation and observation may no longer be adequate. In this context, scientists may need to adopt a more philosophical approach to cosmology, considering multiple dimensions of reality and exploring theoretical frameworks that allow for new ways of understanding the universe, even without the constraints of empirical validation. Ultimately, the ongoing debate surrounding pre-Big Bang theories enriches scientific methodology by underscoring the importance of interdisciplinary collaboration, By merging insights from cosmology, physics, and even philosophy, researchers can develop a more comprehensive understanding of the universe, one that transcends traditional boundaries and opens up new realms of inquiry. This pursuit not only deepens our understanding of the complexities of cosmic origins, but also sharpens our scientific vision, pushing the boundaries of what we consider possible in the exploration of the cosmos. Assumptions, of course, serve as foundational pillars upon which scientific theories are built and explored. When investigating concepts like a pre-Big Bang universe, these assumptions become critically important in shaping the direction of inquiry. Scientists typically begin with a set of established principles about the nature of the universe, including the laws of physics and the fundamental properties of time and space. These principles guide the questions scientists ask and influence the interpretations they make about the cosmos's origins. One of the most significant assumptions in modern cosmology is the belief that the laws of physics, as we understand them today, apply uniformly across both time and space. This assumption forms the basis for many of the models used to describe the evolution of the universe. However, when considering pre-Big Bang theories, scientists are often forced to question whether the laws of physics themselves may have evolved over time or whether they might have been entirely different in the earliest moments of the cosmos. This fundamental uncertainty challenges the very framework upon which current scientific inquiry is based, encouraging researchers to think beyond conventional models and explore new paradigms for understanding the true nature of reality. However, when we venture into the deep and enigmatic realms of what might have existed before the Big Bang, we find ourselves facing some of the most profound challenges in modern cosmology. Many theories suggest that our conventional understanding of time and space might not be applicable in the same way before the Big Bang, because that very event marks the inception of time as we know it. This prompts fundamental questions about causality, the flow of time, and the nature of existence itself. Could there have been a time without time? What conditions could have prevailed in the absence of our universe's current framework? Theories such as the cyclic universe, the multiverse, and the idea of quantum fluctuations offer intriguing possibilities for what may have transpired before the Big Bang. Each of these theories is grounded in specific assumptions about the nature of reality, and those assumptions lead to wildly divergent interpretations of the universe's origin. For instance, the cyclic universe model proposes that the cosmos undergoes an eternal cycle of birth, death, and rebirth. According to this theory, the Big Bang we observe is simply the latest in a series of cosmic bounces, each marking the beginning of a new cycle, with time itself being a product of this ongoing cycle rather than a linear progression from a single origin. Meanwhile, the multiverse theory suggests that our observable universe might be just one among many, each with its own distinct properties and laws of physics. In this model, the Big Bang could be seen as the formation of one bubble in a vast, ever-expanding multiverse. This perspective radically alters how we think about not just the origins of our universe, but also the fundamental nature of reality itself. Could our universe be just one of countless others, each existing in parallel and perhaps governed by entirely different principles? Then there are the theories of quantum fluctuations, which suggest that the conditions before the Big Bang could have been shaped by quantum events, tiny, unpredictable fluctuations that could have triggered the rapid expansion we now call the Big Bang. These fluctuations, governed by the strange and counterintuitive laws of quantum mechanics, might not only have set the stage for the universe's birth, but could have existed in a state that defies our current understanding of time and space. These various hypotheses underscore the complexity and ambiguity of our search for the origins of the cosmos. The assumptions embedded within each theory, whether cyclical, multiversal, or quantum, offer contrasting visions of the pre-Big Bang universe, each with unique implications for how we interpret the birth of everything we observe. As scientists continue to debate and refine these theories, the questions only grow more profound, opening up new avenues of inquiry into the very fabric of reality itself. As researchers delve deeper into these speculative realms, they must constantly adapt their models to incorporate new discoveries and technological advancements. The evolution of cosmology is a dynamic process, with theories shifting in response to fresh data and innovative ideas. For instance, the rise of quantum physics and string theory has led to revolutionary developments in our understanding of the universe's origins. These emerging ideas challenge traditional concepts of space-time and demand more sophisticated models that can account for the strange, often paradoxical behavior of matter and energy at the quantum level. One of the most exciting and complex areas of exploration is the integration of quantum gravity into the cosmological model. Quantum gravity seeks to reconcile the principles of quantum mechanics with the force of gravity, an endeavor that has long eluded physicists. The theory of loop quantum gravity, for example, suggests that time and space might behave in fundamentally different ways at the smallest scales, possibly offering insights into the very nature of the Big Bang itself. If quantum gravity can provide a coherent description of the universe's origins, it could completely alter our understanding of space, time, and causality. But adapting these models to account for such novel concepts is no simple task. It requires a delicate balance between observed evidence, theoretical consistency, and mathematical rigor. As new observational tools and techniques like gravitational wave detectors and advanced space telescopes provide a wealth of data, scientists are continually revising their models to reflect these findings. Each new discovery, whether it's the detection of cosmic microwave background radiation or a deeper understanding of dark matter, brings us closer to piecing together the puzzle of the universe's early moments. In this sense, scientific inquiry is a constantly evolving process where theories are tested, refined, or replaced as our understanding grows. The pursuit of understanding the pre-Big Bang universe is not only a scientific challenge, but also a philosophical one. What does it mean to speak of a time before time? Can we even frame meaningful questions about the state of the universe before the Big Bang? Or are we limited by the very structure of our language and understanding? These questions stretch the boundaries of both science and philosophy, demanding new ways of thinking about existence itself. In this grand quest, mathematics plays an indispensable role. It is the language of the cosmos, the tool that enables us to translate abstract ideas into rigorous models. Equations derived from general relativity, for example, allow us to understand the curvature of space-time and time, and to make predictions about how the universe might behave under extreme conditions, such as those that might have existed before the Big Bang. Through mathematical methods, scientists can explore phenomena like singularities and quantum fluctuations, essential elements for understanding the state of the universe at its inception. Similarly, computer science plays a critical role in the advancement of cosmological theories. With the help of advanced algorithms and vast computational power, researchers can simulate complex scenarios that might have occurred in the early universe. These simulations allow scientists to test various hypotheses and explore the implications of different models, from the behavior of quantum fields to the dynamics of cosmic inflation. In some cases, the equations used to describe the universe are so complex that only computers are capable of solving them, revealing insights that would be otherwise unattainable. The intersection of mathematics, computer science, and theoretical physics is particularly evident in areas like string theory and loop quantum gravity. String theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings, requires highly sophisticated mathematical tools and computational methods to explore its implications. Similarly, loop quantum gravity, which seeks to unify quantum mechanics with gravity, involves intricate calculations that often necessitate the use of advanced computer simulations. As scientists continue to push the boundaries of knowledge, the collaboration between these fields will become increasingly important. The synergy between mathematicians, physicists, computer scientists, and philosophers is crucial to unraveling the mysteries of the pre-Big Bang universe. Each discipline brings its own strengths and insights, contributing to a holistic understanding of the cosmos. Physicists provide the theoretical frameworks, mathematicians offer the rigorous models, and philosophers challenge our assumptions about reality, prompting us to reconsider the very nature of existence. Ultimately, the journey to understand the origins of the universe is one of collective effort, where multiple disciplines work in concert to answer the most fundamental questions about the cosmos. As our understanding evolves, so too does our conception of the universe's birth, revealing new layers of complexity and wonder at every turn. Through continued collaboration and innovation, we inch ever closer to unlocking the secrets of the universe's earliest moments, secrets that may forever alter our view of reality. Interdisciplinary teams often collaborate in experimental design, where diverse expertise converges to create innovative tests for complex theoretical frameworks. For instance, astronomers leverage powerful telescopes and advanced detection methods to gather observational data that may validate or challenge pre-Big Bang models. This collaboration ensures that the tests they develop are scientifically robust and practically feasible, further enhancing the credibility of their findings. The role of these interdisciplinary efforts in developing tests for theories about the origins of the universe cannot be overstated. By combining insights and methodologies from different scientific fields, researchers can address profound questions about the universe's beginnings with greater creativity, rigor, and precision. As our understanding of the cosmos continues to evolve, these collaborative efforts will likely illuminate even more hidden mysteries, tucked away behind the cosmic curtain of time and space. The study of the universe's origins is an inherently complex and multifaceted endeavor, one that greatly benefits from the collective wisdom of researchers across various scientific disciplines. Physicists, astronomers, chemists, geologists, and even biologists all play vital roles in reconstructing the history of the universe from its inception to the present day. Each discipline brings a unique perspective, offering specialized tools and methodologies that contribute to a more comprehensive understanding of cosmological phenomena. Physicists often take the lead in investigating fundamental concepts such as dark matter and dark energy, two mysterious forces that together account for a significant portion of the universe's composition. Using theoretical models and powerful particle accelerators, they simulate conditions that mirror those of the universe shortly after the Big Bang. In parallel, astronomers gather light from distant galaxies, study the cosmic microwave background radiation, and examine supernovae, all critical sources of information that help validate or challenge the predictions made by physicists. Their observations provide invaluable data on the universe's expansion, age, and early conditions. Chemists, too, are integral to this multidisciplinary approach. They study the elemental composition of celestial bodies and the chemical processes occurring in stars and nebulae. This information is crucial for understanding the creation of the universe's first elements and how these elements have evolved through phenomena like star formation and supernova events. Geologists contribute by examining planetary bodies within our solar system, providing insight into the geological history that shapes our understanding of conditions conducive to life. Their work helps clarify how life might have originated on Earth, offering context to the larger questions of cosmic development. Through the exchange of data, techniques, and findings, researchers from various fields create a richer, more nuanced picture of the universe's origins. Collaborative studies and conferences foster dialogue and the cross-pollination of ideas, driving the formulation of innovative theories. This integration of knowledge not only deepens our understanding of the cosmos, but also sparks new questions, prompting further inquiry into the unknown aspects of the universe. In this sense, the collective effort of diverse scientific disciplines fuels an ongoing cycle of discovery that propels forward the narrative of the universe's evolution. Recent astronomical breakthroughs have significantly expanded our understanding of the cosmos, reigniting discussions about the conditions that might have existed prior to the Big Bang. One of the most compelling revelations comes from the study of cosmic microwave background radiation, the faint remnants of the early universe. These observations provide crucial insights into the universe's evolution and have even suggested possible scenarios that challenge traditional perception of aliens. Another fascinating development lies in the detection of gravitational waves, ripples in space-time, first observed in 2015. These waves have opened new frontiers in physics, offering clues about the fabric of space-time itself, and suggesting that certain gravitational wave signatures may point to events occurring before the Big Bang. This leads to intriguing theories about a cyclical universe, with endless phases of expansion and contraction, suggesting a rhythm of cosmic rebirth. Moreover, advancements in telescope technology, particularly with instruments like the James Webb Space Telescope, have enabled astronomers to peer deeper into the universe than ever before. With this unprecedented level of detail, scientists are uncovering galaxies that formed just a few 100 million years after the Big Bang. These discoveries challenge the idea of a simple, singular origin point for the universe, suggesting a far more intricate history that may stretch beyond the traditional scope of the Big Bang theory. Additionally, dark matter and dark energy remain enigmatic yet dominant components of the cosmos. Despite their pervasive influence, they remain largely elusive to direct observation. Understanding the behavior and interactions of these substances is key to unraveling not only the structure of the universe, but also the nature of what might have existed before the universe itself came into being. Each new discovery in these fields provides more pieces to the grand cosmic puzzle, expanding our comprehension of the universe's origins and inviting further contemplation on what lies beyond our current understanding. Recent cosmic discoveries continue to reshape and refine our theoretical models of the universe. For example, the detection of gravitational waves has opened a new window into the study of black holes and neutron stars, reinforcing certain aspects of Einstein's theory of general relativity while also challenging classical notions of these phenomena. These findings not only confirm long-held beliefs, but also add new layers of complexity to our understanding of space-time. The discovery of exoplanets, especially those situated in the habitable zones of their stars, has profound implications for the search for extraterrestrial life. These discoveries support and expand existing theories of planetary formation and evolution, prompting scientists to refine their models of how planets form and develop under various conditions. This has led to more sophisticated predictions regarding where life might exist in the universe. The dynamic interplay between new discoveries and evolving theories reveals the ever-changing nature of scientific inquiry. In addition, the application of cutting-edge technologies, such as deep space telescopes, has vastly expanded our observational capabilities, enabling us to detect previously undetectable cosmic phenomena. The data and images these instruments provide are helping to reinforce the Big Bang theory, offering concrete evidence of cosmic microwave background radiation and the formation of distant galaxies. As a result, scientists are not only confirming existing models, but are also expanding them to incorporate new, groundbreaking astronomical observations. This continuous flow of discovery and innovation propels forward our understanding of the universe's origins and ensures that our exploration of the cosmos remains a dynamic and ever-evolving pursuit. The interactions between groundbreaking discoveries and theoretical models serve as a powerful reflection of the scientific process itself, an ever-evolving journey driven by the constant need to adapt and refine our understanding of the cosmos. This process thrives on revision, on the constant rebirth of ideas as new data emerges. As our understanding deepens, models are adjusted and theory refined, shedding light on the extraordinary flexibility and complexity inherent in the scientific method. The continuous evolution of these models ensures that our grasp of the universe not only remains accurate, but also grows increasingly profound, offering new insights with each passing year. These insights, in turn, fuel humanity's insatiable quest for knowledge about the cosmos, pushing the boundaries of what we know and sparking curiosity about the unknown. The story of the universe's origins is far from static. It is a constantly unfolding narrative, shaped by a cascade of new discoveries and advancements in science. Each breakthrough, whether related to cosmic microwave background radiation, the formation of galaxies, or the mysterious behavior of dark energy, adds a new layer to our understanding of how the universe began and evolved over billions of years. Scientists engage in a meticulous process of analysis, interpreting these findings and placing them within a larger, interconnected framework that seeks to link seemingly disparate pieces of data. It is a process that never ceases to evolve, as new information invites fresh interpretations, challenging old assumptions and illuminating new possibilities. Around 11 billion years ago, the universe emerged from a singularity during the event known as the Big Bang. This cataclysmic moment set into motion a chain of events that would shape the cosmos as we know it. Since then, a rich tapestry of cosmic phenomena, from stellar explosions to the formation of black holes, has played a pivotal role in sculpting the universe's vast and intricate structure. Each new piece of data, whether it comes from telescopes or satellite missions, provides new insights that must be integrated with existing theories. For example, findings from the Hubble Space Telescope or the Planck satellite can either strengthen current models or, alternatively, challenge established views, prompting scientists to rethink the very foundations of our understanding. This process of integration is not a solitary endeavor. Scientists from around the globe regularly convene at workshops and conferences to share their insights, discuss new findings, and refine existing theories. These gatherings serve as critical platforms for collaboration where ideas are debated, tested, and reshaped. It is often in these discussions that groundbreaking theories emerge, leading to a reevaluation of fundamental aspects of the cosmic narrative. Sometimes, these new ideas stretch the boundaries of what we thought we knew, leading to breakthroughs that shape the future of cosmological research. The publication of findings in scientific journals plays a vital role in ensuring that new knowledge is shared, scrutinized, and ultimately integrated into the broader scientific discourse. As new layers of understanding emerge, the narrative of the universe's origins grows ever richer. It is like an intricate puzzle, each new discovery providing another piece that enhances the overall picture of our cosmos. This dynamic process invites both scientists and non-scientists alike to marvel at the vast, uncharted territories of the universe. The more we learn, the more we realize just how much remains to be discovered. It is a never-ending journey, one that draws us closer to the heart of existence itself. Symmetry plays a pivotal role in our understanding of the universe, particularly when we venture into theories that address the era before the Big Bang. In physics, symmetry is the principle that certain properties remain unchanged even as other factors shift. For example, if you rotate a sphere, its appearance does not alter, it remains invariant under transformation. This idea of symmetry helps scientists formulate theories about the nature of reality prior to the Big Bang, proposing that the universe may have been governed by laws that were symmetrically balanced, with forces, matter, and energy all existing in harmony. In the realm of cosmology, this concept of symmetry helps physicists build models of the early universe. One key theory posits that the universe began in a highly symmetric state where the fundamental forces, gravity, electromagnetism, the strong force, and the weak force, were unified, indistinguishable from one another. In such a state, the universe would have been in a cosmic equilibrium, with all forces acting in perfect balance. If the universe indeed began in such a highly symmetric state, it could provide insights into how the forces that govern the cosmos evolved as the universe expanded and cooled. One of the most significant pieces of evidence supporting this theory comes from the uniformity observed in the cosmic microwave background radiation. This faint glow, which permeates the universe, offers a snapshot of the early universe, when it was still in its infancy, just a few 100,000 years after the Big Bang. The near-perfect symmetry in the cosmic microwave background radiation suggests that the universe may have been in a state of near-perfect uniformity at its earliest moments, aligning with the theory of an inflationary period when space expanded exponentially in the blink of an eye. However, the absence of symmetry introduces an entirely different set of possibilities. If the universe before the Big Bang lacked symmetry, it could have led to diverse interactions and variations in the distribution of matter and energy. The breaking of symmetry could have triggered a cascade of chaotic events that set the stage for the complexity and structure we see today. Understanding how symmetry was broken and what consequences this had for the evolution of the cosmos is key to understanding the universe's origins. It could reveal why, after the Big Bang, the universe evolved into a state that is anything but uniform, with galaxies, stars, and planets forming through a dynamic and highly complex process. In this context, the interplay of symmetry and asymmetry provides an endless realm of exploration, offering tantalizing clues about the fundamental forces that shape our reality. These theories not only contribute to our understanding of cosmic inception, but also serve as a bridge between our current knowledge and the profound mysteries of the universe's earliest moments. The quest to unravel the true nature of the universe, its origins, and the forces that govern it is far from over. It is a journey that will continue to unfold, revealing new depths of understanding and inviting us to push the boundaries of human knowledge ever further. Cosmology, the study of the origins and structure of the universe, has long been intertwined with questions of symmetry and the forces that govern the cosmos. One of the most compelling theories that has emerged from this vast field is the concept of cosmic inflation. This idea postulates that in the moments just after the Big Bang, the universe experienced an extraordinarily rapid expansion, an inflationary phase that stretched the cosmos to unimaginable sizes in a fraction of a second. This explosive growth didn't just increase the size of the universe, it also smoothed out irregularities in space, leading to a more homogeneous state where symmetry could take hold. These very fluctuations, however, may have seeded the vast cosmic structures we observe today, including galaxies. By investigating the cosmic microwave background radiation, scientists can peer into these early moments of the universe, revealing remnants of symmetry breaking that carry clues about the state of the cosmos near its inception. This faint radiation, the afterglow of the Big Bang, provides a canvas upon which we can trace the imprints of these initial fluctuations. Symmetry, as it turns out, plays a central role in understanding not only the early universe, but also the universe as a whole. When scientists probe the fundamental forces and structures that shape our reality, they are often not just exploring a single point in time, but a vast landscape of possibilities, each one leading to a different configuration of the universe. As researchers continue to unravel the mysteries of the cosmos, the role of symmetry-based theories becomes ever clearer. These theories suggest that the fundamental forces of nature operate under unifying principles of symmetry, which govern the behavior of everything from elementary particles to the grand structures of the universe. The standard model of particle physics, for instance, looks at the interactions between fundamental particles and seeks patterns that align with the notion of symmetry. By understanding these patterns, scientists are able to better unify the different forces that shape reality. A pivotal discovery in this context was the Higgs boson, a particle found in 2012 at the Large Hadron Collider. This elusive particle plays a crucial role in the Standard Model as it supports the mechanism that gives mass to other fundamental particles. By studying the Higgs boson, its behavior, its interactions with other particles, and how it decays, physicists can confirm or challenge the validity of their symmetry theories, taking us one step closer to understanding the fundamental forces that govern our universe. In tandem with the study of the Higgs boson, cosmic microwave background radiation remains one of the most valuable tools in cosmology. This faint glow, which permeates the universe, is the last remaining trace of the Big Bang. By analyzing the uniformity and slight variations within this radiation, scientists can glean information about the universe's earliest moments. These subtle fluctuations can help determine whether the expansion of the universe and the distribution of matter align with the predictions of symmetry-based theories, revealing deeper truths about the nature of cosmic origins. Similarly, the distribution and evolution of galaxies serve as a natural laboratory for testing symmetry theories. Galaxies, as vast collections of stars, gas, and dark matter, exhibit patterns that may reveal underlying principles of symmetry. If these theories hold, we would expect to see regularities in how galaxies cluster and evolve over time. By mapping these structures and observing their movement across the cosmos, astronomers can refine their models and deepen their understanding of the universe's large-scale architecture. However, the investigation of the universe's origins goes beyond empirical data and into the realm of abstract thinking. When scientists consider the universe before the Big Bang, they encounter a challenging paradox. Traditional physics and observational methods hit a brick wall. It's here that mathematics becomes a crucial tool, allowing theorists to explore scenarios that transcend the observable universe. Frameworks such as string theory and quantum gravity provide mathematical structures that define the parameters of the early universe and allow for the formulation of hypotheses that stretch beyond current understanding. These abstract constructs offer potential models in which space and time themselves might behave in radically different ways, opening the door to new interpretations of existence itself. Some of the most fascinating ideas to emerge from this speculative landscape are theories of the multiverse and the cyclical universe. According to these concepts, our universe may not be a unique occurrence, but part of an endless series of cosmic cycles, each one marked by a Big Bang followed by a cosmic contraction and rebirth. In this model, time itself becomes a cyclical process with no true beginning or end. Alternatively, the multiverse theory posits that our universe is just one of countless others, each with its own set of physical laws and constants. In this view, what came before the Big Bang might not be describable in terms of our current understanding of existence. Rather, it might belong to a realm of other universes, potentially older or even radically different from our own. The concept of the multiverse challenges everything we thought we knew about reality. If true, it suggests that our universe is only a tiny chapter in a much larger, incomprehensible story, a story that stretches beyond the limits of imagination. Such ideas, though speculative, offer a rich field for exploration and provoke some of the most profound questions about our origins and our place in the grand scheme of existence. In this search for knowledge, the role of abstract thinking cannot be overstated. It allows scientists to step beyond the bounds of immediate observation and into the realm of theoretical exploration. Concepts like dark matter, black holes, and quantum particles are not directly observable, yet they form the cornerstone of our understanding of the cosmos. Through the lens of abstraction, scientists can propose and test models that account for these phenomena, building frameworks that predict how the universe behaves under extreme conditions. Moreover, abstract thinking plays a pivotal role in synthesizing knowledge across multiple disciplines. By drawing on fields as diverse as physics, cosmology, and philosophy, scientists create a more holistic picture of the universe. This interconnected approach leads to a deeper understanding of the cosmos and fuels the quest to uncover its most fundamental secrets. As we ask ever more profound questions about the origins of the universe, abstract thinking propels us forward, encouraging innovation and discovery at the frontiers of human knowledge. Yet, the journey to understand the universe's origins begins with the Big Bang itself, a moment widely recognized as the birth of space and time as we know it. From this hot, dense state, the universe expanded rapidly, setting into motion the forces and structures that would shape the cosmos. But this raises a tantalizing question. What, if anything, existed before the Big Bang? While the answers remain elusive, several theories attempt to fill in the gaps. One such theory is cosmic inflation, which posits that the universe underwent a massive, rapid expansion shortly after the Big Bang. Some versions of this theory even suggest that this inflationary phase might have been part of a larger cyclic process in which the universe undergoes endless cycles of expansion and contraction. In this model, each Big Bang is merely the beginning of a new cycle, leading to an eternally reborn cosmos. The multiverse theory offers another fascinating possibility, suggesting that our universe is just one of many within a vast, possibly infinite sea of universes. Each universe could have its own set of physical laws, and some may even precede ours, hinting at a realm beyond the Big Bang, a place where our concepts of time and space no longer apply. If this theory holds true, the idea of a singular origin for our universe may be far too simplistic, offering instead a much more complex and mysterious framework for understanding the cosmos. In the end, these theories, whether they speak of cyclic universes, parallel worlds, or uncharted realms, invite us to think beyond the limits of our current knowledge. The universe, it seems, may be far more vast and complex than we can even imagine, with the Big Bang merely serving as one chapter in an eternal, ever-expanding story. Quantum mechanics, with its enigmatic and often mind-bending principles, opens the door to ideas that challenge the very core of our understanding of reality. One of the most profound contributions to this field comes from the celebrated physicist Stephen Hawking, who put forward an astonishing idea that the universe has no boundary. In his groundbreaking work, Hawking proposed that quantum fluctuations, tiny, unpredictable variations in the energy of the vacuum, could give rise to scenarios in which time itself did not exist as we understand it before the Big Bang. This theory fundamentally shakes the foundations of our perceptions of causality, suggesting that time might not have been a linear progression from past to present, but rather an entirely different concept altogether. This line of thinking, which merges the worlds of quantum mechanics and cosmology, forces us to reconsider the very fabric of existence. If the universe emerged from a quantum state where the usual rules of logic and causality don't necessarily apply, then what does that say about our understanding of the universe's origins? Hawking's ideas push us to think beyond conventional notions of creation, asking us to question whether the universe, as we know it, is merely one of many possible outcomes of a quantum event. And then there's the fascinating concept of the multiverse, a speculative theory that has captivated the minds of cosmologists for years. The idea behind the multiverse is that our universe, with its unique properties and laws of physics, might not be the only one. Rather, it could be just one of an infinite number of universes, each with its own distinct characteristics. Some theorists suggest that these universes could have emerged from quantum fluctuations within a vast cosmic landscape, each one an isolated bubble in a never-ending expanse. This mind-stretching idea flips our notion of existence on its head, leading to the thought-provoking possibility that the Big Bang wasn't a singular beginning, but rather a transition between different universes, each experiencing its own cycle of birth and death. Another intriguing speculative theory is the concept of cyclic universes. This model proposes that the universe undergoes an endless series of expansions and contractions, akin to a cosmic heartbeat. Each cycle begins with a Big Bang and ends with a big crunch, only for the process to begin anew. This vision of the cosmos challenges the conventional understanding of time, suggesting that the universe is not a one-time event, but rather an eternal cycle that is woven into the very fabric of existence. It offers an enticing framework for theorists eager to understand how the universe could regenerate itself, constantly evolving through time and space. Building on these ideas, some theorists have looked to string theory to propose a pre-Big Bang scenario. In this view, the fundamental building blocks of reality are not particles, but tiny, vibrating strings, each carrying its own unique properties. String cosmology suggests that before the Big Bang, the universe may have existed in a completely different state, one that was governed by different physical laws and higher dimensional spaces. This pre-universe could have been a kind of cosmic soup, containing fluctuations that eventually led to the formation of the universe we observe today. These ideas introduce a vision of the cosmos that stretches far beyond our conventional understanding of time and space, challenging us to rethink what came before the Big Bang. As we delve deeper into these speculative theories, it becomes clear that they offer a glimpse into a new way of thinking about the universe, a universe that may not be bound by the limits of our current knowledge. These theories invite us to consider the possibility that existence itself is far more mysterious and complex than we have ever imagined. The quest to understand the conditions that existed before the Big Bang is one that has intrigued cosmologists for decades. And though we have yet to find concrete evidence to support these ideas, the search continues to fuel our curiosity and wonder. However, speculative theories often face significant challenges, particularly when it comes to empirical validation. In science, validation refers to the process of using observation and experimentation to support a hypothesis. But many speculative ideas, such as those involving alternate dimensions or the intricate nature of quantum fluctuations, are extremely difficult, if not impossible, to test with current technology. This creates a major obstacle in building the kind of evidence needed to either confirm or refute these theories. Furthermore, for a scientific theory to hold weight, it must be falsifiable. This means that there should be a potential observation or experiment that could prove the theory wrong. But many speculative theories, by their very nature, involve ideas that are so abstract or so grand in scale that they cannot be easily tested or measured. Concepts like parallel universes or exotic forms of matter may seem compelling, but they do not lend themselves to straightforward experimentation. As a result, these ideas often remain in the realm of philosophical debate rather than empirical science. Another issue arises when speculative theories challenge established scientific frameworks. When a new idea is proposed, it can sometimes contradict existing theories that are already backed by solid empirical data. This creates a conflict within the scientific community, as new ideas must be evaluated within the context of what we already know. Theories that cannot easily be integrated into established models often face skepticism, which can slow their acceptance and limit further research and testing. This conservative approach, while essential for maintaining scientific rigor, can sometimes stifle innovation and delay the exploration of new possibilities. Despite these challenges, the allure of speculative theories lies in their ability to stretch our imagination and push the boundaries of what we know. Whether they lead to groundbreaking discoveries or remain as intriguing puzzles, these theories force us to reconsider the nature of reality itself. They inspire us to keep asking big questions, challenging our assumptions, and seeking answers that may one day redefine our place in the cosmos. For now, the mysteries of what happened before the Big Bang remain tantalizingly out of reach, but the pursuit of knowledge continues, driving humanity to uncover the secrets of the universe, one theory at a time. Speculative research in science often faces significant challenges, particularly in securing the funding and resources necessary for such ambitious projects. These scientific endeavors, especially those exploring uncharted realms of knowledge, demand substantial financial investment. However, funding bodies typically prioritize proposals with well-defined, achievable goals that are grounded in existing knowledge. Speculative theories, by their very nature, do not always fit into this mold. These bold ideas may seem too abstract or unproven to justify the resources required for their exploration, making it difficult for researchers to pursue them. As a result, many potentially groundbreaking ideas remain in the realm of theory, unable to progress due to these financial limitations. Thus, the journey of scientific discovery, while often marked by daring innovation and groundbreaking theories, is frequently hampered by a complex web of factors: skepticism, the need for validation, and crucially the challenge of securing the necessary funding to explore these ideas. Concepts such as cosmic strings and membranes, represent some of the most fascinating and ambitious areas of theoretical physics. These ideas have the potential to reshape our understanding of the universe, but their speculative nature often places them in direct conflict with the practical realities of scientific funding. Cosmic strings, for example, are theoretical structures that could have formed during the early moments of the universe, possibly as defects in the fabric of space-time. They are one-dimensional objects that might have arisen from phase transitions as the universe cooled following the Big Bang. To visualize this, imagine cracks forming in ice as it freezes. Cosmic strings might have similarly emerged during the cooling of the universe. Though unconfirmed, the very idea of cosmic strings challenges our understanding of the early universe, and, if they exist, would have profound implications for cosmology. These theoretical objects could reveal critical details about the origins of matter and the distribution of energy in the cosmos, possibly leaving a distinct signature in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. These strings might have created specific gravitational waves that would cause fluctuations detectable in the CMB. If cosmic strings exist, their influence on the early universe could be observed through subtle temperature variations in this radiation. Furthermore, scientists are examining the large-scale structure of the universe, looking for signs that cosmic strings might have shaped the distribution and movement of galaxies. By studying these patterns, researchers hope to find clues that could confirm the existence of these elusive structures. While direct evidence remains a challenge, advancements in observational technology continue to push the boundaries of what is possible, offering new opportunities to gather supporting data. Cosmic strings represent a compelling area of research, but they are only one aspect of the theoretical landscape. Brains, a central concept in string theory, offer another exciting avenue for exploring the universe's origins. According to string theory, the fundamental components of nature are not point-like particles as traditionally understood, but rather tiny vibrating strings. Within this framework, our universe may be nothing more than a three-dimensional brain existing within a higher dimensional space. This model suggests that the universe we observe is only a small part of a much larger multiverse, one that includes additional dimensions beyond the familiar three dimensions of space and one of time. In some versions of brain cosmology, our universe's creation is tied to the collision of two brains in this higher dimensional space. Such a collision could release immense amounts of energy, giving birth to the universe as we know it. This concept offers a unique perspective on the Big Bang, proposing that the event itself might have been the result of a higher dimensional interaction rather than the explosive singularity traditionally envisioned. This collision could also explain the ongoing expansion of the universe, a phenomenon that aligns with current observational evidence of cosmic growth. Furthermore, brain cosmology provides a potential framework for resolving some of the most perplexing issues in physics, such as the nature of black holes and singularities. In traditional models, black holes are seen as the ultimate endpoint of collapsing matter. However, in the context of brain cosmology, black holes may be viewed not as endpoints, but as integral components of the brain structure itself. This perspective could offer new insights into how universes evolve over time, suggesting that the behavior of black holes might be more closely tied to the larger architecture of the cosmos than previously understood. As a developing theory, brain cosmology continues to evolve and engage with other established theories, bridging the gap between our current understanding and new groundbreaking ideas about the universe. This innovative approach has the potential to revolutionize our understanding of cosmic origins, suggesting that our universe is just one part of a much more intricate and interconnected reality. In addition to cosmic strings and brains, another important concept in theoretical physics is the role of quantum fluctuations in shaping the universe's earliest moments. Quantum fluctuations are tiny, random changes in energy that occur even in what we consider the vacuum of space. While this may seem abstract, quantum fluctuations play a crucial role in the creation of the universe. Prior to the Big Bang, the universe as we know it did not exist in the conventional sense. However, quantum mechanics suggests that even in the vacuum state, energy was never perfectly zero. Instead, there were always fluctuations, a kind of background noise, which set the stage for everything that followed. One theory posits that these quantum fluctuations could have given rise to regions with slightly higher energy density, leading to a rapid expansion that eventually resulted in the Big Bang itself. This rapid expansion, known as inflation, would have established the fundamental characteristics of the universe as we know it today. Furthermore, these fluctuations are thought to be responsible for the uniformity and distribution of matter in the cosmos, as the tiny quantum fluctuations were stretched to cosmic scales during inflation. The imprint of these fluctuations can still be detected today in the cosmic microwave background radiation, which carries valuable information about the early universe. By studying these fluctuations, scientists can gain important insights into the conditions that existed before the Big Bang. This research not only sheds light on the origins of our universe, but also offers a deeper understanding of the fundamental nature of reality itself. Finally, the concept of energy levels plays a pivotal role in understanding the pre-Big Bang universe. Energy levels refer to the discrete amounts of energy that a system, such as an atom or subatomic particle, can possess. In the context of cosmology, energy levels help theorists visualize the conditions that might have existed before the Big Bang. One hypothesis suggests that the universe may have originated from an extremely high energy state, possibly involving a quantum vacuum. This vacuum, far from being empty, was filled with fluctuating energy levels that could have led to the creation of virtual particles. As the universe began to expand, these energy levels would have changed, eventually giving rise to the matter and energy that make up the universe today. Understanding how these energy levels shifted helps scientists model the early stages of the universe's evolution, particularly during the period of rapid inflation. As the universe cooled, the energy density decreased, leading to the formation of fundamental particles and eventually atoms. These particles would later combine to form the stars, galaxies, and planets that make up the universe we observe today. The exploration of quantum fluctuations and energy levels, while still highly theoretical, provides a fascinating glimpse into the universe's origins. These ideas challenge our understanding of time and space, suggesting that the very laws of physics might have been fundamentally different in the moments before the Big Bang. As researchers continue to investigate these concepts, they open the door to a deeper understanding of the universe, one that reaches beyond the boundaries of what we currently perceive. The exploration of energy levels in the universe holds profound implications, not only for our understanding of cosmic phenomena, but also for the quest to find a unified theory of physics. By investigating these energy states, scientists are attempting to bridge the gap between two fundamental pillars of modern physics: general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which operates at the subatomic level. This intersection may hold the key to solving one of the greatest mysteries in physics: how to reconcile the seemingly disparate realms of the very large and the very small. Insights gained from these investigations could provide crucial clues not only about the conditions preceding the Big Bang, but also about the very nature of reality itself. They challenge our most basic conceptions of time, space, and existence. In this pursuit, new theories regarding energetic events and fluctuations are reshaping our understanding of the universe's origins. For much of modern history, the Big Bang theory has served as the prevailing explanation for the commencement of the universe. According to this view, the Big Bang was a singular event, marking the beginning of both time and space. This idea suggests that everything, from galaxies to stars to planets, began from a singular starting point. However, emerging frameworks in cosmology are now questioning this linear narrative. They propose that the universe may not have had a single, distinct beginning, but instead has evolved through a series of energetic events that have spurred cosmic development over time. One of the most influential concepts in this emerging paradigm is the theory of cosmic inflation. This theory posits that shortly after the Big Bang, the universe underwent an incredibly rapid expansion, an inflationary phase during which energy densities fluctuated wildly. These fluctuations did not merely set the stage for the formation of cosmic structures, they became integral to understanding how the universe evolved in the billions of years since. Instead of seeing the universe as having a clean, singular origin, researchers are now exploring the idea that energy states have fluctuated in a far more complex manner, leading to a nonlinear, ever-evolving cosmos. This new understanding of energetic fluctuations is not just a prelude to the formation of matter. It suggests that the evolution of the cosmos could be far more intricate and far-reaching than previously thought. Moreover, the fascinating domain of quantum mechanics introduces another level of complexity. In quantum mechanics, even what appears to be empty space, seemingly nothingness, is teeming with energy. This idea opens up the possibility that the cosmos may have been born from quantum fluctuations, potentially hinting at alternative mechanisms of creation. Instead of a one-time singular event, the universe could have experienced cycles of creation and destruction, with each cycle building upon the previous one, creating an infinitely rich tapestry of existence. As these theories continue to unfold, they challenge our preconceived notions of the universe. Rather than viewing the cosmos as the result of a singular event, we may come to see it as a dynamic, ongoing process, a perpetual interplay of energy and forces that fuels continuous cosmic evolution. This new lens invites us to reconsider our place in the universe, encouraging us to explore what we thought we knew about the cosmos and pushing the boundaries of our understanding. The concept of alternate dimensions adds another layer of intrigue to the picture. In traditional cosmology, the Big Bang is considered the starting point of not only the universe, but also of space and time. However, theories suggesting the existence of alternate dimensions offer a radically different perspective. These theories propose that our universe could be just one of many, part of a vast multiverse, where each universe may be governed by its own set of physical laws and constants. These ideas often draw upon string theory, which postulates that fundamental particles are not point-like objects, but rather tiny, vibrating strings. According to string theory, our familiar three-dimensional space is just one part of a higher dimensional reality, potentially involving many more spatial dimensions. In this framework, the universe before the Big Bang could have existed in a higher dimensional space, with properties and dynamics vastly different from what we experience today. This opens up the possibility that the Big Bang itself was not the true beginning of everything, but rather a transition point, a burst of energy triggered by the interaction or collision of different dimensions or even entire universes. Such events could have released enormous amounts of energy, creating the conditions necessary for our universe to emerge. This multiverse perspective also introduces the idea that different universes could have entirely different physical laws, leading to unique realities that are fundamentally distinct from our own. Some models suggest that the constants we observe in our universe, such as the strength of gravity or the mass of fundamental particles, could have arisen randomly from a vast array of possibilities, shaped by the interactions between different universes or dimensions. This randomness might explain why our universe is governed by the specific laws of physics that we observe, offering an explanation that is not limited to a single, immutable origin. The concept of alternate dimensions challenges our conventional understanding of existence. Instead of seeing our universe as a singular, isolated entity, we are invited to consider it as part of a broader, interconnected web of realities, each with its own history and set of physical laws. This perspective opens up new avenues for scientific exploration, encouraging us to look beyond the known and explore the untapped possibilities of the cosmos. Incorporating extra dimensions into our understanding of the universe, as proposed by theories such as string theory, could profoundly change our view of the universe's earliest moments. String theory suggests that the fundamental building blocks of matter are not particles, but tiny vibrating strings. These strings require additional spatial dimensions beyond the three familiar dimensions of space and one of time. If such dimensions exist, they could provide an entirely new framework for understanding the nature of space-time itself. Extra dimensions may reveal a landscape in which our universe is just one of many, arising from the interactions and configurations of these higher dimensional spaces. Such a scenario could provide a far more complex picture of the universe's birth, where the Big Bang is not a singular event, but rather the outcome of the dynamics between various dimensions. The traditional view suggests that the Big Bang was a singularity, a point where space and time as we know them came into existence. However, the introduction of extra dimensions may offer a richer narrative, where space itself may have been structured differently in the pre-Big Bang era. In some models, the interactions between these extra dimensions could have triggered the expansion of our universe, initiating the process of inflation. This rapid, exponential expansion would have smoothed out the irregularities in the early universe, setting the stage for the cosmic structures that would eventually form. The energy released during these interactions could have been the catalyst for the rapid growth of space, shaping the universe we observe today. The notion of extra dimensions and alternate realities expands our understanding of the cosmos in ways that challenge the very fabric of existence. Instead of a single, isolated origin, the universe may have arisen from a more complex, multifaceted reality. Through this lens, the Big Bang becomes not just a singular event, but one chapter in an ongoing, dynamic process that continues to unfold across vast stretches of time and space. This framework invites scientists and cosmologists to rethink the fundamental nature of the universe and its origins, and to explore the myriad possibilities that may lie beyond the boundaries of our current understanding. While we currently lack concrete evidence to confirm the existence of extra dimensions, the implications of their potential presence are profoundly significant. These possibilities challenge the very nature of reality itself and compel us to reconsider the origins of the universe, raising questions about what existed before the Big Bang. Understanding this pre-Big Bang state could fundamentally alter our grasp of existence, revealing a hidden realm that is both mysterious and extraordinary. This profound shift in cosmic understanding continues to drive physicists and cosmologists alike, encouraging them to delve deeper into these tantalizing concepts. Their pursuit of answers fuels a relentless quest for a more comprehensive understanding of the universe. In particular, physicists often turn to theories involving higher dimensions to explain the complex phenomena occurring in the cosmos. In the three-dimensional world we are familiar with, we easily visualize length, width, and height. However, when contemplating ideas like string theory or M theory, the concept of extra dimensions becomes essential to grasping the full scope of the universe. These frameworks suggest that the number of dimensions could increase to 10 or even 11, far surpassing the familiar 3. The twist, however, lies in the nature of these extra dimensions. They are believed to be compactified or tightly curled in such a way that they remain imperceptible to our senses. Current technology cannot detect them, leaving us with only theoretical tools to understand their potential existence. One of the main purposes of these additional dimensions is to unify the fundamental forces of nature, forces like gravity and electromagnetism. To make sense of this unification, physicists use intricate mathematical models that describe how particles and forces interact in these extra-dimensional frameworks. These equations allow scientists to probe the very essence of matter and energy in ways traditional theories cannot, offering a deeper and richer understanding of the universe's workings. For instance, in the realm of string theory, particles are no longer viewed as tiny, indivisible points. Instead, they are envisioned as minuscule, vibrating strings. The frequency at which these strings vibrate determines the type of particle they represent, with different vibrational patterns giving rise to different fundamental particles. To help visualize these extra dimensions, scientists often use analogies. One such analogy involves a garden hose. From a distance, the hose appears to have only one dimension, a simple line. However, upon closer inspection, one can observe that its surface has two-dimensional texture. In a similar manner, higher dimensions could be folded or compactified in such a way that they are not immediately perceptible to our three-dimensional senses. These models help scientists predict the behavior of particles at high energies, particularly in extreme environments such as the early universe or deep space. Though the idea of extra dimensions can seem mind-boggling, it opens new pathways for understanding the cosmos. Experiments conducted in particle accelerators and advances in cosmology continue to align with these theoretical frameworks, offering potential evidence for the existence of these elusive dimensions. The pursuit of these higher dimensional models represents a fundamental aspect of humanity's unyielding quest to uncover the underlying fabric of reality itself. In parallel, the enigmatic components of dark matter and dark energy further complicate our understanding of the universe, particularly when we begin to explore what may have existed prior to the birth of the cosmos. Dark matter, an invisible substance that makes up about 27% of the universe, cannot be seen through conventional means. It neither emits, absorbs, nor reflects light. Its existence is inferred through the gravitational effects it has on visible matter, such as galaxies. Dark energy, on the other hand, constitutes approximately 73% of the universe and is believed to be responsible for the accelerated expansion we observe today. Understanding these two cosmic phenomena not only offers insight into the universe's structure, but also challenges us to contemplate what existed before the Big Bang. Research into dark matter suggests that it plays a crucial role in the formation and cohesion of galaxies. Acting like a scaffold, dark matter's gravitational influence helps hold galaxies together, shaping the evolution of cosmic structures. This evidence suggests that dark matter may be tied to physical processes that occurred long before the Big Bang, potentially offering a window into the universe's origins. The interactions caused by dark matter could have set the conditions for the Big Bang itself, prompting speculation about whether dark matter has always existed or whether it emerged from some more fundamental state. Dark energy introduces yet another layer of complexity into this cosmic puzzle. The uniformity of dark energy throughout the universe could imply that it has been a consistent force throughout the history of the cosmos, possibly even playing a role in shaping the conditions that preceded the Big Bang. This raises intriguing hypotheses about the energy dynamics of the universe, suggesting that the current expansion may be a residual effect of the early universe's dynamics. Dark matter and dark energy together hint at a cosmic landscape that transcends our current understanding of time and space, compelling researchers to explore models that extend beyond the traditional Big Bang framework. As we delve deeper into these mysteries, we move ever closer to answering the fundamental question of what existed just before the universe began its expansive journey. The pursuit of understanding dark matter and dark energy offers new insights into the very fabric of reality, transforming our comprehension of everything that surrounds us. This quest for knowledge is as much about the present as it is about the past, as it provides crucial information that could forever change how we view our place in the cosmos. Astrophysicists are actively investigating pre-Big Bang scenarios, exploring how dark matter and dark energy might have played pivotal roles in shaping the universe's evolution. One area of exploration is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, as traditionally imagined, but tiny, vibrating strings. This revolutionary idea has led to investigations into how dark matter might manifest in a pre-Big Bang state. The theory suggests that dark matter could have played a key role in the rapid cosmic inflation that occurred just after the Big Bang, setting the stage for the universe we know today. Another important avenue of research involves sophisticated simulations and modeling that account for the effects of dark energy. By examining how dark energy may have influenced the fabric of space-time and the formation of cosmic structures before the Big Bang, scientists are developing new models that could provide deeper insight into the early universe's conditions. These models aim to simulate various cosmic scenarios, testing their consistency with existing cosmological data. If successful, these simulations could provide evidence that links dark energy with the fundamental forces that shaped the universe's early history. In this ongoing search for answers, the exploration of dark matter, dark energy, and extra dimensions opens new doors to understanding the cosmos. It invites us to think beyond the boundaries of our current knowledge, challenging established theories, and encouraging a broader perspective on the universe's origins and the fundamental nature of reality. Through these groundbreaking investigations, scientists continue to push the frontiers of knowledge, inching ever closer to unraveling the mysteries that have captivated humankind for centuries. Moreover, as our understanding of the universe deepens, observational studies have begun to harness the power of advanced telescopes, with a singular focus on seeking out primordial signals that could offer a glimpse into the behavior of dark matter and dark energy before the Big Bang. This pursuit is not only ambitious, but deeply complex. Scientists aim to study the cosmic microwave background, CMB, radiation, and gravitational waves, two of the most telling traces left by the early universe. By analyzing these faint echoes of the universe's infancy, they hope to uncover patterns, anomalies, or even subtle clues that could unlock the mysteries of these elusive cosmic forces. Despite our rapidly growing technological capabilities, the search for dark matter and dark energy continues to raise profound questions, which bridge the gap between the beginning of the universe and its possible predecessors. These mysterious entities, dark matter and dark energy, are critical in shaping the evolution of the cosmos, yet they remain shrouded in obscurity. Collectively, they account for nearly 95% of the universe's total mass and energy, yet conventional detection methods remain unable to reveal their presence directly. Instead, scientists infer their existence by observing their gravitational effects on visible matter, such as galaxies and galaxy clusters. This indirect detection method raises important questions about the very composition of the universe, challenging long-established models and pushing the boundaries of modern physics. When we turn our attention to the origins of the universe, particularly in relation to the Big Bang Theory, the absence of direct evidence for dark matter and dark energy complicates our understanding of how everything began. These components play a crucial role in the universe's evolution. For instance, dark matter is thought to act as the invisible scaffolding that holds galaxies together, while dark energy is believed to drive the accelerated expansion of space itself. Without a clear, direct understanding of these cosmic forces, our theories about the formation and evolution of the universe remain incomplete, like a jigsaw puzzle missing its most important pieces. The quest to uncover the true nature of dark matter and dark energy has ignited an explosion of new scientific inquiries and innovations. Researchers are developing an array of cutting-edge experiments and instruments designed to probe the universe across multiple wavelengths and extreme conditions. This multidisciplinary approach not only expands our knowledge of these elusive components, but also presents a fundamental challenge to our understanding of the laws of physics themselves. The possibility of groundbreaking discoveries about the universe's inception looms large. In this sense, the elusive nature of dark matter and dark energy serves as both a monumental hurdle and a driving force in our quest for knowledge. As we attempt to unlock their secrets, we inch ever closer to a more comprehensive narrative about the birth and evolution of the universe, one that could potentially reshape our very understanding of existence itself. Cosmic anomalies, such as unexpected irregularities in the cosmic microwave background radiation, odd distributions of galaxies, and variations in the distribution of dark matter, serve as crucial pieces of the vast cosmic puzzle. These anomalies offer tantalizing insights into the conditions that might have existed before the Big Bang. By examining them closely, scientists hope to piece together clues about the physical forces and processes that shaped our universe long before it began its explosive expansion. One particularly notable example of these anomalies is the slight imperfections in the cosmic microwave background radiation. While this radiation is often regarded as the afterglow of the Big Bang, its slightly uneven temperature fluctuations suggest that the early universe was anything but uniform. These irregularities point to a much more chaotic and dynamic beginning, possibly influenced by conditions that predate the Big Bang itself. Some scientists theorize that these temperature fluctuations could be remnants of a far grander cosmic structure, or even a multiverse, offering a tantalizing glimpse into the possibility that our universe is just one of many, each with its own set of physical laws. This theory of a multiverse, an endless number of universes, each different from the last, has gained traction as researchers delve deeper into these anomalies. If such theories are correct, it would mean that the Big Bang was not the singular beginning of everything, but rather a specific event within a much broader and more intricate cosmic context. This could completely revolutionize our understanding of the universe's origins and its place within a potentially infinite and ever-expanding multiverse. As we continue to observe these cosmic anomalies and gather more data, the quest to understand the true nature of dark matter, dark energy, and the universe itself is only beginning. What we learn in the coming years may not only fill in the missing gaps of our theories, but could also lead to an entirely new framework for understanding the very fabric of reality. In many ways, we are still standing at the edge of a profound discovery, one that could unlock the deepest mysteries of the cosmos. The distribution of galaxies across the universe reveals intricate patterns that suggest anomalies in the fabric of cosmic structure. These irregular groupings challenge our conventional understanding, urging scientists to investigate whether forces beyond simple chance are at play. Rather than appearing randomly scattered throughout space, galaxies often seem to cluster in unexpected ways, forming vast superclusters and filaments that stretch across the cosmos. These observations raise profound questions about the universe's underlying structure and the forces that shaped it, suggesting that the conditions of the universe prior to the Big Bang may have been far more complex than previously thought. This possibility introduces a provocative idea. What if the universe existed in a vastly different form before it began its rapid expansion? Such anomalies in galaxy distribution could be remnants of a pre-existing cosmic order, pointing to structures that were in place long before the Big Bang. This concept challenges our conventional understanding of time, space, and causality, inviting us to reconsider the very nature of reality itself. As astronomers continue to explore these cosmic mysteries, they may uncover insights that fundamentally alter our understanding of the universe. Each discovery offers the potential to reshape our theories of cosmology, expanding the boundaries of our knowledge and forcing us to reconsider everything we thought we knew. In the pursuit of understanding the universe's origins, we are not simply uncovering facts. We are engaging in a journey of intellectual discovery, one that stretches both the limits of human imagination and our capacity to comprehend the cosmos. The search for answers to the question of what existed before the Big Bang is not only a scientific endeavor, it is a philosophical one. It requires us to grapple with ideas that push the boundaries of reason and challenge our very understanding of existence. As we probe deeper into the mysteries of dark matter, dark energy, and the accelerating expansion of the universe, we are forced to confront the limitations of our current models and to contemplate new ways of interpreting the cosmos. Among the most perplexing phenomena that challenge our current understanding are the mysterious forces known as dark matter and dark energy. These invisible substances account for the majority of the universe's mass and energy, yet we have little direct knowledge of their nature. Dark matter, which constitutes about 27% of the universe, does not emit, absorb, or reflect light, making it nearly impossible to detect with traditional instruments. Its existence is inferred through its gravitational effects on visible matter, as well as on the cosmic microwave background radiation. This enigmatic substance has forced astronomers to reconsider classical models of gravity, adding an entirely new layer of complexity to our understanding of the universe's behavior. Similarly, dark energy, which is believed to make up about 70% of the universe, is thought to be responsible for the accelerating expansion of the cosmos. This discovery was a shocking twist for astronomers who had long expected that gravitational forces would slow the expansion of the universe over time. Instead, dark energy seems to act as a repulsive force, pushing galaxies apart at an ever-increasing rate. The introduction of dark energy into our cosmological models has forced scientists to revise their theories about the fate and structure of the universe, suggesting that the cosmos is far more dynamic and unpredictable than previously assumed. The quest to understand dark energy remains one of the most significant challenges in modern cosmology. It has opened up new frontiers in fundamental physics, inviting researchers to explore theories that were once considered speculative or fringe. The continued study of these phenomena not only tests the limits of our current knowledge, but also fuels the development of new theories, each one potentially bringing us closer to a unified understanding of the universe. As we uncover new insights into the nature of dark matter and dark energy, we are reminded that the cosmos is filled with mysteries that continue to challenge our most fundamental assumptions. This ongoing process of discovery and refinement is a testament to the dynamic nature of science. It is a constant cycle of testing, questioning, and revising our understanding of the universe. Each new observation provides an opportunity to expand our knowledge, pushing us ever closer to a deeper understanding of the cosmos and our place within it. The process may be slow and fraught with uncertainty, but it is through this rigorous approach that we continue to unravel the mysteries of the universe, one discovery at a time. The study of cosmic anomalies plays a crucial role in this process. Anomalies, unexpected data points or observations that don't fit within established theories, often serve as the catalyst for new discoveries. Rather than dismissing these irregularities, scientists approach them with a sense of curiosity and open-mindedness, recognizing that they could provide the key to understanding some of the universe's most profound secrets. When scientists encounter such anomalies, the first step is to verify the data. Researchers meticulously examine their instruments, checking for errors or malfunctions that could explain the unusual results. Once they are confident in the integrity of the data, they begin to explore possible explanations, developing hypotheses that can account for the unexpected observations. These hypotheses can range from minor adjustments to existing theories to entirely new ideas that challenge the very foundations of cosmology. If an anomaly suggests that our understanding of dark matter or the rate of cosmic expansion is incorrect, researchers may propose alternative models that better explain the data. Each hypothesis undergoes rigorous testing, with scientists scrutinizing both the new evidence and the existing body of knowledge to ensure that any proposed theory fits within the broader framework of cosmological understanding. Only when the data supports a compelling new explanation does the scientific community begin to accept it, potentially leading to paradigm shifts in our understanding of the universe. History is filled with examples of key discoveries that have emerged from the study of anomalies. The existence of dark matter, the mysterious properties of the cosmic microwave background radiation, and the unexpected acceleration of the universe's expansion all began with puzzling observations that could not be explained by existing theories. These discoveries have fundamentally changed our view of the universe, illustrating the importance of questioning, testing, and refining our understanding of the cosmos. As scientists continue to explore the mysteries of the universe, they are not only expanding our knowledge, they are also demonstrating the true power of human curiosity and ingenuity. Another fascinating concept that challenges our understanding of the universe is cosmic recycling. This idea refers to the processes of birth, evolution, and eventual death of stars, galaxies, and other celestial bodies. Rather than existing in a static state, the universe is in a constant state of flux, with matter and energy continuously being transformed. At the heart of cosmic recycling is the life cycle of stars. When stars exhaust their nuclear fuel, they do not simply fade away. Instead, they explode in dramatic supernovae, scattering elements like carbon, oxygen, and iron throughout space. This material then coalesces to form new stars, planets, and even life, creating a continuous cycle of creation and destruction. Cosmic recycling also offers intriguing insights into what might have existed before the Big Bang. Some cosmological models propose that the universe undergoes infinite cycles of expansion and contraction, known as the cyclic model. According to this theory, the universe may have collapsed and re-expanded multiple times throughout history, with each cycle recycling matter and energy from the previous universe. In this scenario, the remnants of past universes would have contributed to the material that formed our own universe, adding another layer of complexity to our understanding of cosmic evolution. This concept of cosmic recycling challenges our traditional understanding of the universe as a single linear event. Instead, it suggests that the cosmos may be part of an ongoing process, one that transcends individual lifetimes and spans across countless cycles of creation and destruction. Whether or not this theory is correct, it serves as a reminder that the universe is far more complex and mysterious than we often realize, with each new discovery revealing deeper layers of understanding and inviting us to ponder the nature of existence itself. Moreover, this idea radically challenges the conventional notion that the Big Bang marks a singular, definitive beginning of everything we know. Rather than viewing it as the start of all things, the concepts of cosmic recycling and the cyclic model encourage us to think of the universe as part of an ongoing, eternal process. This perspective suggests that the universe's life cycle might stretch far beyond what we currently regard as its origin, opening up a wealth of theories about what came before and possibly what will come after our universe as we know it. At the core of this idea is the suggestion that the universe could be eternal, continuously evolving through an infinite number of transformations. It's an understanding that not only questions the concept of a linear beginning, but also points to a universe that might exist in a constant state of flux, where death and rebirth are perpetual cyclical events. Recent cosmological research has turned its attention toward dark matter and dark energy, those mysterious, unseen forces that account for most of the universe's mass and energy. These elements could play pivotal roles in this cosmic recycling, acting as both the materials and the force sources that drive the perpetual renewal of the universe itself. Exploring the concept of cosmic recycling enriches our understanding of the universe's life cycle. It encourages us to consider the universe not as a static entity frozen in time, but as a vibrant, ever-evolving tapestry. This ongoing transformation is woven from the remnants of previous epochs, from long-dead stars whose ashes have been reincorporated into new celestial bodies. These recycling models suggest a universe that never truly ends, constantly regenerating and reshaping itself across immense timescales. At the heart of these models lies the belief that the universe is not a one-time event. Rather, it is a dynamic system, a cosmic engine that continually churns through processes of birth, death, and renewal. Stars are born from vast interstellar clouds, live out their luminous lifespans, and eventually die, their remnants spreading new life into the cosmos. This echoes the cyclical theories of the universe, which propose that the cosmos undergoes repeated phases of expansion and contraction. According to such models, the universe may collapse in on itself at some point before being reborn in another Big Bang-like event, creating an endless loop of cosmic evolution. By merging the ideas of recycling with the rhythm of creation and destruction, we can imagine a universe that perpetually reinvents itself. An even more fascinating layer of complexity emerges when we examine the intersection between cosmic recycling and multiverse theories. Multiverse theories suggest that our universe is not the only one. There could be an infinite number of universes, each with its own unique laws of physics and set of possibilities. In this context, cosmic recycling might not be confined to just one universe. Instead, it could be a widespread process occurring across multiple universes, with each universe recycling its matter and energy in its own way. These processes could lead to the formation of diverse cosmic structures, some similar to ours and others radically different. This interconnection between recycling and the multiverse opens up the thrilling possibility that the very byproducts of one universe's recycling could influence others, potentially altering the laws of physics in ways we have yet to even imagine. What if the remnants of one universe gave rise to new laws that governed another? What if the products of cosmic recycling sparked the creation of exotic particles or phenomena that defy our current understanding of reality? Such notions are not just thought experiments, but represent the kind of frontier thinking that drives modern theoretical astrophysics. As we explore these ideas further, the implications become ever more profound. The merging of cosmic recycling, cyclic theories, and multiverse concepts invites us to rethink the entire nature of existence. If our universe is merely one among many, then the process of recycling and rebirth could span beyond our universe's borders, touching countless others in ways we can't yet comprehend. It raises a fundamental question. What is the true scope of the universe's existence, and how does our understanding of it change when we consider it as part of a much larger and far-reaching system? The study of these interwoven concepts opens the door to mind-bending possibilities. By exploring the dynamics of cosmic recycling and how it interacts with theories of cyclical universes and the multiverse, scientists and cosmologists are pushing the boundaries of our knowledge. It challenges our most basic assumptions about the universe's origin, existence, and ultimate fate. The very creativity and mystery embedded in these ideas push us to continually question and reimagine what we think we know, inspiring a quest for understanding that could one day redefine our reality. In practical terms, cosmic recycling theories propose a vision of the universe's future in which the death of stars plays a pivotal role. As stars live and die, the materials they expel, hydrogen, carbon, and other essential elements, are scattered back into space. These materials then become the building blocks for new stars, planets, and potentially even life itself. It's a continuous cycle of birth and rebirth, with each generation of stars leaving behind the raw materials needed to form the next. This ongoing process of cosmic recycling ensures that the universe remains dynamic and full of potential. As the universe ages, the nature of this cycle will change. Initially, stars form from clouds of gas and dust spread throughout galaxies, often taking billions of years to coalesce into fully fledged stars. Over time, these clouds are enriched with heavier elements, a byproduct of earlier generations of stars that have exploded in supernovae. This enrichment will lead to the formation of new stars that are fundamentally different from their predecessors. Instead of just burning hydrogen, they may rely on a variety of heavier elements, creating stars that could support more complex structures. This gradual shift will lead to a universe where the potential for life, perhaps even life forms vastly different from anything we know, becomes increasingly likely, all driven by the ongoing recycling of cosmic materials. In the grand scheme of things, cosmic recycling offers a profound shift in how we perceive the universe's life cycle. No longer just a story of birth and death, It paints a picture of a universe engaged in a continuous process of regeneration, where every end is a prelude to something new and wonderful. Through this lens, the universe becomes not a one-off event, but a dynamic, ever-evolving system, rich with possibilities waiting to unfold across the eons. Cosmic recycling not only shapes the evolution of galaxies and stars, but it also offers profound insights into the ultimate fate of the universe. As the cosmos continues its ever-expanding journey, some theories speculate that stars, the very engines of energy and light, will eventually run out of fuel. This depletion of resources could lead to a scenario known as the cold, dark universe, a vision of the distant future where stellar formations cease entirely. In this scenario, the once brilliant and dynamic cosmos would transform into a vast, cold, and dark expanse, filled with the remnants of stars that have long burned out. These remnants would include white dwarfs, neutron stars, and black holes, each a silent witness to the universe's former vibrancy. Over time, even these stellar remnants would slowly fade, leaving behind an empty void where energy is scarce and life as we know it has been extinguished. In this future, the universe would be characterized by a gradual, inexorable decline in activity. The once dynamic interplay of creation and destruction, which defined the early years of the universe, would give way to a quiet, still expanse. The universe would become a place where only echoes of the past remain, scattered across an otherwise barren void. The cycle of cosmic recycling thus serves not only as a reminder of the universe's rich history, but also as a stark preview of the future trajectory it may follow, urging us to contemplate the ultimate destiny of everything that exists. This contemplation naturally leads us to the no-boundary proposal, an intriguing concept put forth by the legendary physicist Stephen Hawking and his collaborator James Hartle. The proposal offers a new way of thinking about the universe's origins, attempting to describe the very conditions of the cosmos at its inception. Rather than subscribing to the traditional notion of a singular starting point, Hawking and Hartle's theory imagines the universe as having no boundaries, much like the surface of a sphere. To illustrate this, consider the Earth. Its surface is finite but lacks any edges, dropping off into nothingness. In a similar way, the no-boundary proposal suggests that the universe is finite yet does not have a conventional boundary, neither in time nor space. This idea proposes that time, as we understand it, did not exist in its familiar form before the Big Bang. In fact, prior to this event, time as we know it ceases to function in any meaningful way. Instead, the universe existed in what is called quantum geometry, a smooth transition from an imaginary time to the real time we experience. Within this framework, the universe did not emerge from a singular moment of creation. Instead, it existed in a state of potential, with an infinite array of possible configurations, each representing a different way in which the cosmos could have unfolded. This concept of a boundaryless universe defies conventional ideas of before and after, offering a radically different view of the origins of reality itself. One of the most captivating elements of the no-boundary proposal is its challenge to traditional ideas about the beginning of the universe. The theory suggests that the universe did not emerge from a single point of infinite density, what we traditionally call a singularity, but instead arose from a quantum state devoid of clear boundaries. This eliminates some of the paradoxes that arise when trying to reconcile singularity-based models with modern physics. In this framework, the universe's beginning is not marked by a sudden flash of creation, but by a seamless transition from the realm of potential into the reality of existence. Furthermore, the no-boundary proposal ties into the broader scientific understanding of the cosmos, particularly through its connection to quantum mechanics. In quantum theory, multiple potential states can exist simultaneously, and Hawking and Hartle's model incorporates this principle to suggest that quantum fluctuations played a crucial role in the universe's birth. These fluctuations could have served as the seeds for the universe's rapid expansion, leading to the formation of galaxies, stars, and planets as we observe today. The idea that the universe could emerge from a quantum state without a singular beginning offers a smoother and more coherent explanation than traditional models, which often struggle with the contradictions and anomalies associated with singularities. However, this radical proposal is not without its critics. Some scientists argue that the no-boundary proposal's reliance on quantum mechanics makes it difficult to reconcile with the observable universe. For example, the distribution of galaxies and the cosmic microwave background radiation seem to suggest that the universe originated from more structured and defined initial conditions. Critics contend that while the no-boundary model is elegant, it may be too abstract to fully account for the detailed and predictable phenomena we observe in the universe today. They question how events like the formation of galaxies and the pattern of cosmic radiation could arise from a boundaryless, quantum-based beginning. Despite these criticisms, the no-boundary proposal remains a crucial part of ongoing cosmological research, as scientists continue to explore the earliest moments of the universe's existence. One area of particular interest is its potential connection to the concept of cosmic inflation, a rapid and exponential expansion of space that occurred within fractions of a second after the Big Bang. This idea suggests that the universe underwent a period of intense growth, shaping the large-scale structure of the cosmos as we see it today. The no-boundary proposal, with its emphasis on quantum mechanics and smooth transitions from one state to another, provides a compelling framework for understanding how the universe evolved during these formative moments. The no-boundary concept ultimately challenges the very nature of existence and the boundaries of our understanding of reality. It forces us to think beyond the traditional notions of time, space, and creation. By contemplating a universe without a boundary, we not only delve into the mysteries of how the cosmos began, but also question the very nature of what it means for something to exist at all. The proposal sparks curiosity and wonder, pushing the boundaries of our imagination as we attempt to comprehend the origins of the universe and ultimately our place within it. This groundbreaking theory is a testament to the ever-evolving dialogue in cosmology, opening up new paths of inquiry about the universe's beginnings. While the no-boundary proposal may not provide all the answers, it represents a crucial step in our journey to understand the cosmos, a journey that continues to captivate the minds of scientists, philosophers, and curious minds alike. By transforming real time into imaginary time, mathematical models soften the otherwise unyielding nature of singularities. This shift in perspective suggests that rather than an explosive and chaotic beginning, the universe might have transitioned gradually from a timeless state into the expansive cosmos we see today. This shift is not just a technical adjustment. It presents a radically different narrative about the origins of the universe. Instead of envisioning time as a simple, linear progression originating from a distinct, momentous beginning, the no-boundary idea allows us to consider the universe's origin as a more complex, nuanced process. It opens up the possibility that the cosmos could exist without any clearly defined starting point. Such a view challenges conventional notions of time and space and invites a re-evaluation of our understanding of reality itself. This framework offers a profound opportunity to rethink the nature of the universe. It suggests that the cosmos may not have had an explosive origin, but instead could have emerged from an undifferentiated, timeless state. This could imply a smoother, less violent transition into the cosmos we recognize, suggesting that singularities, often considered the violent, chaotic beginnings of the universe, might not be as destructive or final as we once thought. This theoretical shift proposes a different model of the cosmos's early stages, where time may not be an inherent feature, but rather an emerging condition that gives rise to the universe as we know it. The idea pushes us to reconsider what constitutes the beginning of the universe, challenging the assumption that it must be tied to a singular, explosive event. However, exploring the universe before the Big Bang presents numerous challenges, primarily due to our limited understanding of what occurred during this primordial epoch. Central to these challenges is the very nature of time, which may not have functioned in the way we understand it today. Traditional physics, grounded in the concept of time as a continuous measurable flow, encounters significant difficulties when confronted with the idea of a universe that predates time itself. This creates a paradox. How do we comprehend events or conditions that happened before the concept of time existed, under physical laws that may have been entirely different from those that govern the cosmos now? Moreover, our current understanding of the universe is based heavily on observation, which relies on light and other forms of radiation traveling through space. However, the earliest moments of the universe are hidden behind the cosmic microwave background, CMB radiation, a remnant glow from the Big Bang that envelops the cosmos like a thick fog. This glow serves as a barrier, obscuring any direct observations of the universe's infancy. The CMB effectively shrouds the pre-Big Bang universe, making it impossible to study it through the same observational methods that inform much of modern cosmology. As a result, researchers are left relying heavily on theoretical models to speculate about what may have happened before this critical juncture, but these models remain largely untested due to the absence of empirical data. At the forefront of these theoretical models are ideas such as quantum gravity and string theory, which seek to bridge the gap between the minuscule world of particles and the vastness of cosmic scales. These theories attempt to reconcile the forces governing the microscopic realm with those at play on a galactic scale. Yet, despite their elegance and promise, these theories remain speculative. They lack the empirical validation that typically strengthens scientific concepts, which makes them hard to test against observable phenomena. The challenge is not merely one of formulating these theoretical models, but also of finding ways to validate them, something that remains an elusive goal for researchers. The debate surrounding the interpretation of the evidence also complicates matters further. Various ideas, ranging from cyclical universes to multiverses or quantum fluctuations as precursors to the Big Bang, generate rich discussions but also contribute to the uncertainty. These competing narratives do not just deepen our curiosity, but fundamentally challenge our understanding of physics and reality itself. Are we dealing with a universe that evolves through cycles of birth and death, or is the cosmos a singular event, an anomaly in a far grander multiverse? Could quantum fluctuations be the true catalyst for the Big Bang, or is something entirely different at play? These questions touch upon the very fabric of existence. And as such, each hypothesis carries profound implications for how we understand the universe. In the face of these complexities, researchers continue to push the boundaries of our knowledge, eager to unravel the mysteries of the cosmos. The question of the universe's origin has captivated the minds of scientists for centuries, but even today, many crucial questions remain unanswered. To address these uncertainties, researchers are employing an array of methods that span observational techniques, theoretical models, and experimental physics. One of the most promising avenues of research is the study of cosmic background radiation, which offers a glimpse into the universe's earliest moments. This faint, lingering heat, the afterglow of the Big Bang, provides a snapshot of the universe when it was mere fractions of a second old. By analyzing this radiation, scientists can infer crucial details about the universe's early conditions and the forces that shaped its development. It serves as one of the few direct observational links to the infant universe, offering insights that would otherwise remain hidden. In addition to cosmic background radiation, advanced telescopes and satellites are revolutionizing our ability to observe distant galaxies and cosmic phenomena. Instruments like the James Webb Space Telescope are providing unprecedented views of the cosmos, focusing on the formation of the first stars and galaxies, and offering clues about how the large-scale structure of the universe came into being. By studying the light from distant stars and galaxies, researchers can trace the evolution of the universe over billions of years, piecing together a more complete picture of how the cosmos has evolved since the Big Bang. Another powerful tool in the quest to understand the universe's origin is particle physics. Experiments conducted at facilities like the Large Hadron Collider are recreating the extreme conditions present in the early universe by smashing particles together at incredibly high energies. These experiments seek to uncover the fundamental forces and particles that governed the universe's infancy, potentially offering insights into what happened in the moments immediately after the Big Bang. If successful, they could provide the missing link between the microscopic world of quantum mechanics and the vast, expansive universe we observe today. In sum, while the road to understanding the universe's beginnings is fraught with challenges, new tools and ideas are steadily advancing our knowledge. The quest to unlock the secrets of the cosmos remains one of the most ambitious and profound endeavors in the history of science. And each breakthrough, no matter how small, brings us one step closer to understanding the true nature of reality. Theoretical physicists, driven by an insatiable curiosity about the fundamental nature of reality, are delving into novel concepts that could reshape our understanding of the universe. Among the most ambitious of these ideas are string theory and quantum gravity, frameworks that aim to reconcile the seemingly incompatible principles of quantum mechanics and general relativity. By uniting these pillars of physics, these theories hope to offer a deeper understanding of the fabric of spacetime itself, allowing us to grasp how the universe works at its most fundamental level. As scientists push the boundaries of knowledge, both through new observations and groundbreaking theoretical advancements, they are inching ever closer to unraveling the profound mysteries surrounding the origins of the universe. What began as a quest to understand the cosmos is transforming into a journey that may lead to answers about the very nature of existence itself. Every new discovery weaves a more intricate tapestry, connecting humanity to the vast and mysterious cosmos, showing us that we are part of something far larger than ourselves. Looking ahead, a number of emerging technologies promise to unlock further insights into the universe's beginnings, some of which might challenge everything we think we know. One of the most significant of these advancements lies in the field of gravitational wave astronomy. In 2015, the world watched in awe as scientists confirmed the detection of gravitational waves, ripples in spacetime caused by cataclysmic events such as colliding black holes and neutron stars. These waves carry vital information about the universe, especially the events that occurred shortly after the Big Bang. With continued refinement in detecting and studying these waves, researchers are gaining a new lens through which to view the history of the cosmos, revealing details that were once unimaginable. In parallel, the next generation of telescopes is poised to revolutionize our understanding of the universe. The James Webb Space Telescope, for example, is designed to observe the cosmos in infrared wavelengths. This ability to peer through dust clouds will allow scientists to examine the first galaxies that formed after the Big Bang, revealing critical insights about the evolution of the universe. The telescope's ability to focus on distant celestial objects will provide a wealth of information about the formation of galaxies, stars, and planetary systems, enriching our understanding of the universe's earliest stages. But these advancements don't stop there. As more advanced telescopes come online, they will allow astronomers to address some of the most enduring and perplexing questions about dark matter and dark energy. Two mysterious forces that, despite shaping much of the observable universe, remain largely undetected. These enigmatic components hold the key to understanding the structure and behavior of the universe at the grandest scales. Equally exciting is the field of particle physics, where major upgrades to particle accelerators like the Large Hadron Collider are providing new tools to explore the earliest moments of the universe. By recreating high-energy conditions similar to those just after the Big Bang, these accelerators allow scientists to study the fundamental forces and particles that govern the creation of matter itself. These experiments could provide vital clues about the conditions that led to the universe as we know it, bringing us closer to answering questions that have plagued cosmologists for decades. Advancements in artificial intelligence and machine learning are also having a profound impact on the field of cosmology. As observatories generate vast amounts of data, these technologies enable researchers to sift through the noise, identifying patterns and anomalies that might otherwise go unnoticed. This could lead to the discovery of previously unseen cosmic structures or events, offering fresh perspectives on the universe's origins and our place within it. With AI-powered tools, the sheer volume of data now being analyzed is becoming a treasure trove of new opportunities for scientific discovery. As these innovative technologies continue to evolve, the mysteries of the universe's origins may soon be illuminated in ways that were once the stuff of science fiction. The connection between humanity and the cosmos, once abstract and distant, may become much clearer, offering not just answers to profound questions, but also a deeper connection to the universe that surrounds us. However, when it comes to theories about the pre-Big Bang era, researchers face the challenging task of sifting through a landscape filled with speculative ideas. Most of these theories begin by asking questions based on existing evidence and our current understanding of the universe. Theories that hold the potential to offer new insights into the early cosmos, or that can explain observed anomalies, often rise to the forefront of scientific discussion. This approach encourages a rigorous examination of foundational concepts with the goal of building on the established frameworks of physics. Among the most promising areas of theoretical inquiry are models that align with well-established areas of physics, such as quantum gravity or string theory. These frameworks offer potential mechanisms for understanding the conditions that could have existed before the Big Bang. Theories that integrate well with known physics, while simultaneously filling gaps in our knowledge of the universe's origins, are particularly valued by researchers. The interplay between theoretical abstraction and empirical data is crucial. A compelling theory must withstand scrutiny, not only from the predictions it makes, but also from the observational evidence that supports or contradicts it. Collaborative discussions and debates within the scientific community play a pivotal role in refining and prioritizing theories. Conferences, workshops, and symposia serve as platforms for the exchange of ideas where researchers critique and build upon each other's work. The popularity of a particular theory is not simply a matter of reputation, but rather its feasibility for experimental validation. The most promising theories are those that can eventually be tested through future observations or technological advancements. If a theory can be subject to direct experimental scrutiny, it has a better chance of gaining traction. Thus, the prioritization of pre-Big Bang theories is not a static process. As new data is gathered and existing theories are challenged, the field remains dynamic, with theories constantly evolving to reflect the latest discoveries. This ongoing pursuit of knowledge underscores the scientific community's commitment to both curiosity and rigor, as they continue to search for answers that could shed light on the universe's true beginnings. This journey into the unknown is not just about acquiring knowledge. It is an expression of the intrinsic human drive to understand our place in the cosmos. The pursuit of answers about the origins of the universe is a quest that has captivated the minds of thinkers for centuries. And as scientific advancements continue to push the boundaries of possibility, the answers may soon be within our grasp. What began as a quest to understand the Big Bang itself could ultimately transform our entire understanding of time, space, and existence. However, emerging and groundbreaking theories are prompting scientists to reconsider long-held beliefs, suggesting that the universe may have existed in some form even before the explosive event we call the Big Bang. One particularly fascinating avenue of thought comes from the realm of quantum gravity, a field that attempts to merge the principles of quantum mechanics with the overarching framework of general relativity. Some physicists propose that the universe may undergo cyclical phases, an ongoing dance of expansion and contraction, suggesting that our universe might not have had a singular starting point. Instead, the Big Bang could simply represent the most recent transition in a cosmic cycle that extends infinitely into the past. These cyclical models invite us to imagine a universe that has no true beginning or end, but rather evolves through successive phases, each one a prelude to the next. In this view, the Big Bang may not be an undeniable origin, but just another chapter in an ongoing cosmic story. The implication is profound. Time itself might not flow in a simple, linear progression, and our entire understanding of cosmic history could be far more complex than previously thought. Another compelling theory comes from the enigmatic world of string theory. This groundbreaking concept posits that the fundamental building blocks of the universe are not point-like particles, as traditionally conceived, but rather one-dimensional strings. These strings vibrate at different frequencies, and their various modes of vibration give rise to the particles and forces that we observe in nature. What makes string theory particularly captivating is its ability to suggest the existence of extra dimensions beyond the familiar three that we experience daily. These additional dimensions open up the possibility of intricate, multi-dimensional landscapes that could accommodate conditions prior to the Big Bang. In such a framework, the universe itself may not be a single isolated event, but part of a vast, interconnected web of possibilities, with cosmic creation following entirely different mechanisms than what we have traditionally imagined. These alternative views challenge us to think of the universe not as a single, isolated entity with a definitive beginning, but as a rich, intricate tapestry woven across vast epochs of time. The fabric of the cosmos may stretch far beyond the narrow confines of linear time, urging us to reconsider the very nature of existence itself. As researchers delve deeper into these theoretical realms, they are not only expanding our understanding of the universe's past, but are also pushing the boundaries of human imagination. They are reshaping our perception of time and existence, introducing a more unified and complex vision of the cosmos, one that extends far beyond the limits of our current comprehension. The implications of these theories are profound, compelling us to rethink not only where the universe came from, but also where it is headed. They invite us to confront questions about our own place in the cosmos and how our understanding of reality continues to evolve with each new scientific breakthrough. These advancements, while still speculative in many ways, may ultimately reveal a far more intricate and unified cosmos than we could have ever imagined. Theoretical breakthroughs have always been pivotal in reshaping our understanding of the cosmos and its origins, serving as fresh lenses through which we view the vastness of the universe. Throughout history, significant advancements, such as Newton's laws of motion and Einstein's theory of relativity, have radically altered our perception of how celestial bodies interact and how the universe behaves as a whole. With each new theory comes a cascade of new questions, propelling further research and exploration, enhancing our grasp of the complex phenomena that shape the cosmos. For example, the introduction of concepts like dark matter and dark energy has fundamentally redefined how we perceive the composition of the universe. While visible matter constitutes only a small fraction of the universe, dark matter and dark energy represent nearly 95% of the cosmos energy density, and their existence challenges everything we thought we knew about the universe's structure. These invisible components have become central to modern astrophysics, forcing scientists to rethink not only the makeup of the universe, but also the very laws that govern its operation. Moreover, the development of new theories often arises from the fusion of ideas across multiple scientific disciplines. The ongoing merger of quantum mechanics and general relativity, for instance, stands at the forefront of theoretical inquiry as scientists try to understand how matter and energy behave at both the smallest and largest scales. These cross-disciplinary breakthroughs are pushing the boundaries of what we know, encouraging researchers to craft unified frameworks that can account for everything from the behavior of subatomic particles to the dynamics of entire galaxies. The ultimate goal is a unified theory of everything, one that could tie together the fundamental forces of nature and reveal the true essence of the cosmos. Each new theoretical advancement presents a wave of unanswered questions, inviting further exploration and investigation. These gaps in our understanding often drive the development of new technologies, which in turn enable more precise observation and analysis. As we continue to build upon these theoretical advancements, we move ever closer to unraveling the mysteries of the universe's origins. This ongoing journey of discovery invites both experts and curious minds alike to consider our place in the grand, unfolding tapestry of existence. The universe, in all its complexity, remains a puzzle that humanity continues to explore, striving to decode its mysteries, piece by piece.